Yeah, I looked last time on the last recording. Apparently, I didn't share the screen, so it's just like the video recording for last lecture is just mostly this space and me talking and wandering in and out of the shot. So, apologize for that. Got this set up better now. So, all right. So we ended up finishing last time talking about some expanded output, talking about effect sizes, partial bivariate correlations, partial correlations, and semi-partial correlations, and how those are calculated and interpreted a little bit differently. They're all great measures of effect. Just knowing exactly what they represent and how to go through and interpret those will give you some flexibility in how you're talking about your regression models. So again, this is this extended output with some of your part and partial correlations. Okay, there we go. All right, so for this simple regression model with two predictors, right, we have here our multiple R. This is our multiple correlation. If we square that, we get R squared, right? This tells us the total proportion of variability in our outcome that's shared or attributable to our predictors, right? And so here we've got a really nice model. Whatever's going on, best linear combination of predictors that we have in this model is accounting for close to 62% of the total variability in our outcome. That's pretty good, right? We have our adjusted R square. This is again a correction for small sample. Here you see we've got 24 people, 24 observations in this set. Not very big. We've only got a couple of predictors in this model, so it's not terrible. But anytime you're running a correlation with 24 people, you should probably be worried about that. And you do see a pretty substantial reduction in your adjusted R square, right? Remember that, like, I can't have a negative R square. It can only be positive. So even in the population, if this set of predictors accounts for no variability in my outcome, when I run my sample, it's probably not going to be 0. It's going to be some positive value. And so we get a positive bias here. Okay. Remember conceptually that your R squared is basically your eta squared from what we talked about last semester. Your adjusted R squared is an omega squared. Okay. Just in terms of thinking about sort of making that transfer between what we were doing last semester and what we've got going on in these analyses. Here you got your ANOVA table, right? Your different sums of squares. We talked about where those come from, your different degrees of freedom. And here's your F test. Can someone tell me what's this a test of? This p-value and this F, what's this a test of? What's the null hypothesis being tested in that ANOVA table? Allison, do you remember? Anytime we have a hypothesis test, like almost always, what's a hypothesis test? What's the null hypothesis testing?
There's no relationship or no.
Yeah, there's some value is equal to 0, probably. Almost always it's that something's equal to 0. With this F test, can someone tell me what are we testing is equal to 0 with this?
Prediction?
Sure. Prediction of the model. Yeah, what specific coefficient are we testing? What is it?
I don't know.
The line.
The line. Okay, so yeah, for individual slopes, yeah. Remember, this is just a test of our R squared value, right? This is testing whether or not R squared is equal to 0. Now we've got very small p-value. This is very clearly not a 0 coefficient, right? So this ANOVA table, this is a test of your model. Is my model any good? My model is determined by my R squared. Like, is this accounting for variability in my outcome? Okay, so just make sure you know what's being tested with this. Here we've got large F, very small p-value, and it's saying that, assuming that the population R squared is equal to 0, these data would be very unlikely, right? So we have evidence against that. Okay, so that's what's going on here. Okay. Down here, here's where we have our coefficients, right? We have our unstandardized coefficients. What do our unstandardized coefficients tell us? What's the interpretation of our unstandardized coefficient here? Do you remember?
Isn't that like oh no, I don't remember.
So. What it was for this unstandardized coefficient, we got an unstandardized coefficient of 0.56. What does that tell us?
The variance.
Okay, so this isn't, I mean, this is kind of getting it at variance-ish. What do you think, Jalen?
Doesn't it depend on like if your scales are like the same? Or if they're like different, which one you should use?
Okay, yep, and so that gets into interpreting my standardized coefficient versus my unstandardized coefficient. My raw regression coefficient, what does that tell me?
Oh,
Gabe?
never mind. What?
Go
Sorry,
for it.
wrong. Are you talking about the unstandard? Are you still talking about unstandardized coefficient? I'm sorry.
Yep, unstandardized coefficient, what's this telling us?
Is it like? It's a
Yeah.
regression based on the unstandardized variables or something like that. I don't know. It's like a line.
You're kind of in the right track. Remember, our unstandardized coefficient tell me for every unit increase in X, the associated X, the expected change in Y, right? So here with 0.56, I'm saying, based on this regression model, after I control for X2, for every unit increase in X, I'm expecting to see a 0.56 unit increase in Y. This is our unstandardized coefficient. This is very literally telling us for a unit change, if we were to increase my X predictor 1 unit, how much would we expect Y to increase? Controlling for my other variable there.
This might be kind of a dumb question, but the change in Y is within the like, whatever unit Y is in, or is it?
Y is, yep,
Okay.
we're just talking about raw units here,
Okay.
okay? So what we can't do, and this is what Jalen is getting to or alluding to, is I can't just look at an unstandardized coefficient, and tell if it's big or it's small. Because it really determines about if my X is on a 0 to 5 scale and my Y is on a 0 to 100 scale, that's going to give me a very different coefficient if I'm looking at the same variables as if my X is on a 0 to 10 scale and my Y is on a 0 to 100 scale, something like that, right? So, but what I can do is always interpret this as looking at that saying, based on this model, I'm expecting a 0.56 unit increase in Y, whatever those units are, for every unit increase in X. So it's very, very, very important to think about what a unit increase in X means and what a unit increase in Y means. Incredibly important, okay? Same thing here. After controlling for variability in X1, I would expect every unit increase in X2 to be correspond to a negative or to a 0.01 unit decrease in Y. Now, if I just look at that, that doesn't seem very big relative to variable X. But based on my unstandardized coefficient, I can't say whether it's big or small because it all depends on what a unit is equal to, okay? Here we've got our standard errors, right? And so if I take my coefficient divided by my standard error, what do I get? What do you think, Lisa? I take that value, which is my unstandardized coefficient divided by my standard error, what do I get?
I feel like this is wrong, but the standardized coefficient or no?
Not quite, it's a good guess, right? If I take a coefficient, I divide it by a standard error, what am I getting? Allison? Yeah, it's my t-test, right? Here's my t, my degrees of freedom are for my degrees of freedom here, this is just a testing, it's a t with 21 degrees of freedom, and here's my my coefficient here, okay? Remember that our tests for my predictors in a multiple regression is looking at the unique association of X and Y after I control for everything else, okay? So could I have in the bivariate space a strong correlation between X and Y and throw it in a model and have a regression coefficient that doesn't look like it's contributing anything? Kate, you shook your head. Yes, how can that happen?
About it last
Yeah.
week, so that's why I said yes, but I don't really know how.
Hey, can you give it a shot?
Yeah, so it's accounting for variability well, but maybe the variables are very like similar, like they're accounting for the same thing.
Yeah, exactly. So I could have, here's my outcome, And in bivariate space, here's my predictor, so I'm pretty happy about that, right? These two variables are very highly associated with one another. And so I expect this in the regression model, this is gonna be pretty good, right? But sometimes if I go through and plug it into a regression model, I find that it's not contributing anything to the model. There's no unique, it's not predicting anything unique. Probably what's going on is my other variable is doing something like that, right? Now I've got another, my second predictor is highly overlapping with this one, right? My second predictor is now capturing all of this space, right? So it's coming up as having a small p-value in my model, and so it's making a unique contribution. But X1, only thing that's left here is now this little itty bitty piece up here. It's not doing anything. I've included a predictor that swamped out my other thing. And so now has no unique association once we account for the other stuff, okay? Clinical folks, this starts to become important. Anytime you want to drop a PDI into a regression model, have fun with that, because that's just gonna suck all the air out of the room, right? It's just, you're throwing in a big non-specific distress measure in there, and it's just gonna pull everything out. Experimental folks, same thing. If you were like throw self-esteem or neuroticism or something like that, some big general construct that just is associated with everything. What you might do is if you have a theoretical predictor that's it should hold an association, but it's something that is pretty specific, right? If you just go through and control for non-specific, just like sort of general distress personality, stuff like that, you might not see it have an effect just because that other thing just came in and sucked out all the common variants, right? Which, if you think that that predictor should predict something above and beyond just general common stuff, and it doesn't, then that's a problem. But if that's not what you're expecting to happen, just needing to be mindful of the types of things that we throw into our regression models and do it intentionally, and not just like, oh, no, here's some stuff I have, so we'll just check it out. Okay. So here's our unstandardized. Oh yeah, Danielle.
I understand this concept, but I forgot what you asked. Did you say, is it possible for like to have two predictors not have unique variance? I forgot what you asked.
Okay, so the question was, could I have something that holds a strong bivariate relations with something, but in the context of a regression model, doesn't turn up as evidence of a predictor?
Okay.
And absolutely, right?
Okay.
If it just overlaps too much, yeah.
For the unstandardized coefficient for like the constants, or for like what would be like the contrast, right? Like the
Right.
for coefficients.
Okay, the coefficients that I'm saying.
Yeah, that's up in there.
Yeah.
So like for 0.56, rather than talking in units, could you also talk in percentage, like X is accounting for 56% of the variability in Y, or is that not correct?
Don't do that.
Okay.
Don't do that at all. There is a situation where you can start talking about percentages, but not here. Okay. The general answer is no, not in the way you're talking about things. The other thing that people will do is sometimes they'll take the standardized coefficient, square that, and then interpret that as the proportion of variability in outcome. That's also not correct. Can't do that either. So don't do that. Okay. Our unstandardized coefficient is very literally saying, if I, within this model, after we account for everything else, if I increase my predictor 1 unit, how much of a change would I expect to find? Okay. That's all of it. Talking about units, just raw units here. Okay. My p-values, these are test my unstandardized coefficients. We also have my standardized coefficients. What I can do here is go through and take a look. This is the same interpretation, except now what we're doing is we're just talking about standard deviation units. If I look at my standardized coefficient here, 0.76, this is saying within this model for every standard deviation unit increase in X, I would expect a corresponding about a 3/4 standard deviation unit in Y. Okay. Basically what we're doing, and we'll talk about this, is all SPSS is doing to calculate your standardized coefficients, just taking the z-value, z-scores for your outcome and regressing that onto z-scores of all your predictors, and then just reporting the regression coefficients from that model. And that's going to give you your standardized coefficients. Okay. Standardized coefficients are nice because here, if I look at 0.561, negative 0.011, I don't know which one of those is contributing more stuff. There's no way to know which one of those is a better, stronger predictor in raw units. But if I go to my standardized coefficient, what I can go through and say, okay, this is putting these all on a common scale. So this is very clearly within this model, a stronger predictor of my outcome than X2. Okay, but again, what we would do is we would say, okay, this for every standard deviation unit increase in X, after we control for everything else, we would expect a corresponding 3/4 of a standard deviation increase in Y. Okay. Other thing that will happen too is in terms of your thinking about interpretations. We look at the p-value for X2. What can we say about X2? What do you think, Lindsay?
That it likely overlaps with X1.
Okay, it might, but there's not anything really that we can take a look here. We'd have to compare these coefficients with your bivariate correlation, like your correlation matrix. Looking at your p-value, do we have evidence that X2 is making a unique contribution to this model?
No.
No, right? So we would say, I don't know what's going on in bivariate space. Within the context of this regression model, we're saying that we don't have, these data are not supporting a unique association of X2 with our outcome after we account for X1. Okay. So because of this, do we want to apply strong interpretations to X2? No, right? So this is the thing, wanting to think about when we've got a regression models, particularly if we have a number of variables in our model that's going through and predicting, what you don't need to do is focus on and sort of like grind out, name on the chalkboard over and over again. Give me a literal interpretation of every single thing on there if it's very clearly not a unique contributor, because I really can't say anything about anything. It's ambiguous. I can't tell you one way or the other. Based on these data, we're not saying that X2 has a unique association with the outcome. I'm not saying it doesn't. I'm just saying that these data don't support something that is. So I'm not super interested on saying and learning about like what a 1 unit increase in X2 would, of course, because it just doesn't matter because that's not even close. If we're close, if it's kind of that borderline, maybe we want to think about sort of noting that it's sort of there, right? Is there a real difference between P.06 and P.053? No, it's the same thing, right? So maybe we want to be a little bit flexible there, but just being careful with your interpretations. Okay. So here we've got our standardized coefficients, our test of our unstandardized coefficients, our test of our R-squared, and then we have our part and partial correlations. These are our effect sizes. Here are our bivariate correlations. So yes, Lindsay, you had said, based on sort of this, it looks like there might be some overlap between X1 and X2. Probably, if I look at the bivariate correlation of X2 with my outcome relative to my standardized coefficient. Standardized coefficients, these aren't correlations, these are partial coefficients, but they're still kind of on a similar metric. So yeah, I think probably there's some overlap between X1 and X2, and so X2 is just kind of X1 is swamping everything out, right? And to some extent, X1, but X1 is just a much stronger association overall with XY, right? Here are my partial correlations. Remember, partial correlation is telling me after we pull out everything attributable to other predictors in the model, of that residual variability, what's attributable to my predictor, okay? So here and here we can go through and square these, right? So if I square, someone tell me what 0.772 squared is.
I think 595.
595. Okay. So what this is saying is once we go through and we pull out variability attributable to X2, about 60% of what's left over is shared with X1. Okay. We could go through and do the same for X2, but we're less concerned about that because there's clearly not much going on there. Okay. So the thing about your partial correlation, remember that this is residual variability, right? Of the total piece of the pie of 100%, after I pull out stuff that's attributable to my other predictors, of whatever's left over, what percentage of that, if I square that partial correlation, is attributable to that stuff, okay? So here, I guess, someone squared 0.173.
.029.
So of total piece of the pie, all my variability in my outcome here, right? X2 is uniquely covering about 3%. Okay, so we've got like that piece, right? That's being captured by X2. Now, this isn't associated with a small p-value, so we can't say with the goal, with the system that we've set up, we can't say that X2 holds a unique association with outcome, but in the model, it's capturing about 3% of that, right? So if we pull that out though, of the 97% of the total variability that we started with, about 60% of that is overlapping with X1, right? So something like that, right? So we've got a big piece going on here. Okay. So remember that your partial correlations, you can square them and talk about that as a proportion of residual variability. Again, once we pull out everything else attributable to the model of what's left over, this is what we can go through and talk about. Now, this is hard to kind of wrap your head around and think about, well, I don't know actually just based on that, how much of the total is left. So I don't know here, your residual variability is almost everything. But you could have a situation where the residual variability left over after you pull everything else is only like about 10% of the total outcome, right? It's a different type of situation. So just know how you're how we're interpreting these partial correlations and how they relate to kind of your Venn diagram here. The one thing you can do also with partial correlations, we have benchmarks, right, to kind of generally talk about small, medium, and large. And so this is a nice way if you want to just sort of look at that and look at these in terms of just general magnitude of effect, right? We have benchmarks for that. So, and you don't need to square these to go through and look at this. The one thing that will happen is your partial correlation will often all generally be very close in magnitude as your standardized coefficient or as your standardized coefficient. I've stopped reporting standardized coefficients and partial correlations in the same table because it's functionally redundant information, right? They're a little bit different, they're calculated a little bit different, but it gets a little bit redundant, okay? Did you have a question, Katie?
Yeah, sorry if you've already said this, but zero order, are we paying attention to
That's
that?
bivariate correlation. That's just the correlation of X. Okay. Your part correlation here, this is your semi-partial correlation. Semi-partial correlations are really nice because it's easier to interpret them. You're saying of the total variability in my outcome, what's uniquely shared with my predictor within the context of this model, right? So the denominator for your partial correlation or semi-partial correlation is always 100% of the total variability of your outcome, right? So here, if we go through someone's square 0.75 and tell me what we get.
0.5625.
0.56. And so here we're saying that these two variables or these two percentages are actually pretty close because X2 isn't accounting for much of it. So like the residual variability is almost all of the variability. So these are actually pretty close, but they can be quite discrepant, right? So of the total variability in Y, X1 is accounting for about 56% of the total variability in Y. This is easier to understand and interpret. Like of the total piece of the pie, about 56% is shared with is uniquely attributable to X1. Okay. Problem with now with the semi-partial correlation, we'll talk about this as we get into some power issues. Is your semi-partial correlation, it's hard to know whether or not a semi-partial correlation is there aren't standardized benchmarks for your semi-partial correlation. I mean, you can just look at it and say like, yeah, that's a lot or a little, right? But it just really depends on what else is in the model. Okay. So you've got your zero order, this is your bivariate, this is your partial, this is your part. Okay. And all of these can tell us a little bit different. They're just different ways of looking at our model and thinking about how we understand what's going on. Okay. The thing to remember is anytime we're working with regression, we're looking at unique associations between X and Y after we are accounting for other things in the model. Okay. And recognizing that we can get big shifts depending on the extent to which our predictors are associated with one another. If they're completely orthogonal, my predictors are all correlated 0 with one another, then I have a wonderfully efficient additive model where every variable that I'm going through is grabbing a little bit different piece of the pie. Psychology, though, everything's related to everything. That's rare that we're going to get that sort of situation, right? And so wanting to be very aware of what's happening with this stuff. Okay, yeah.
So it's very crucial that we don't put in like a variable in there that will encompass a lot of stuff, right? And regression, like he said, self-esteem, just because we want to make sure that everything is accounted for properly.
Well, it depends, right? If you're interested in self-esteem, yeah, sure, go ahead and look at self-esteem, right? And if your theory says that, hey, this is something that predicts outcome above and beyond self-esteem, then self-esteem is a great thing to have. What happens, and I'm sort of speaking maybe more to my clinical colleagues than everything else, what someone will want to do is say, oh, well, I want to prove that this predicts something above and beyond depression, right? And so I throw in something like a back depression inventory. Back depression inventory grabs kind of depression, but it also just grabs just general, I'm not feeling good, right? And so what ends up happening is it kind of sucks all the air out of the room. And there's not much left to predict after you go through it and predict something like that if you've got like a distress level. So you just want to be very careful about what you're putting in and making sure that you're being careful with your interpretations.
Okay, so beware of like the scale you use.
Yeah. So just being thoughtful in terms of what you're putting in. And again, this is kind of the heart and soul of regression within the context of psychology, behavioral sciences. We had talked about regression when it was initially developed. It's just a pure predictive model. Like I don't really care what goes into it, so long as it's maximizing my R squared. Because I just want to functionally predict revenue for next year. I couldn't care less why it predicts. If it does, I'm happy about it. That's not the type of research that we do in psychology, right? It's much more theory-based stuff, right? If I can't explain what predictors I have in my model and why they're important, I've got a problem, okay? So, and we'll go through and talk about some different variations on regression that sort of make use of different strategies for doing this. All right. Okay, cool. This is what things look like in Stata. No one cares who's here. All right. Properties of estimators. Okay. Some things to be thinking about when you're reading literature. You'll hear studies talk about different estimators and sort of the properties that make them desirable. One of the things you'll hear is unbiasedness. Unbiasedness, an estimator is going to be unbiased if the expected values of the sample parameters equal the actual population parameter, okay? So if I go through and have some estimator that I'm using to sort of run this regression model, and I have an estimator that I'm saying is unbiased, it says if I were to pull all possible samples of size whatever from the population and sort of go through and run an infinite number of replications of this using all possible samples with replication of size whatever, and I were to plot out the regression coefficients that I got across each one of those replications, the mean of those would be equal to my population value, okay? If I'm unbiased, it means that sort of the aggregate, the sampling distribution of my regression coefficient here is going to, the mean of that is going to be equal to population parameter. Okay, this is the same thing we've talked about all semester when we're talking about the mean as the mean as an unbiased estimate of the population mean. If I were to say, if I were to think about all undergrads on UW campus, right now we're to randomly sample size of 100 and take the mean of those, the mean height of those students, and I were to gather all possible samples of 100 with replacement and take the mean of each one of those samples and plot those mean of those samples, the mean of that distribution would be equal to the population, the actual population mean. If this is a case, if that's a property, if that's what happens with our estimator, we would say that our estimator is unbiased. Okay, so this is different. Remember, if we use population, or if we use the population formula for calculating variance, and if we go through and we use that, that's not an unbiased estimator. It's biased because the mean of all those is not going to be equal to the population mean, right? So we have to do that adjustment where it's n-1 to go through and recognize that we're going to underestimate the population variability and have an adjustment there, right? But if I have an unbiased estimator, it means that the expected value of my sample parameter is equal to the population value. It's not for my individual sample. Can I be confident that my individual sample that I've drawn is equal to the population parameter? Nope, and it almost for sure isn't, right? But I know that over time, if we were to do this over and over and over and over again, the mean of the samples that I could draw will be equal to the population parameter. Gets at unbiasedness. Okay.
I have a question.
Yes.
Why do we have that little EJ?
So the expected value of my sample statistic is equal to the population parameter. Yeah. Okay. Now we can also talk about efficiency. Okay. Efficiency is the inverse of the variability of an estimator, a parameter, where we have smaller variances resulting in greater efficiency. Okay, so let's say that I have two different ways of calculating mean. Hypothetically, I don't, but let's say that I did. Okay, one way, they're both unbiased. If I go through and I sample all possible samples of size 100 of undergraduates on campus, and I take the mean of all of those samples, what I'm going to find is that the average value is equal to the population value with both of these ways of calculating mean, right? But one of those ways has less variability than the other. They're both unbiased, but I've got one estimator that's more efficient because it's less variable, it jumps around, it's a much tighter sort of estimate. Okay, here, when we talked about before, if I just take my sample and I run my regression and I look at my coefficient and I know my coefficient is unbiased, I know that across an infinite number of all possible replications, the average of this value that I've got will equal the actual population parameter. But for this sample that I've collected, am I confident that this sample, that this actual coefficient equals the population parameter? No, probably not. But then I start to think about the efficiency of my estimator. If I have a more efficient estimator, it means that this is going to jump around a whole lot less, which means I'm more confident that this is a better estimator than something that's also unbiased, but I've got more variability in how it goes through and calculates things. Okay. What we see is ordinary least squares. So how we go through and estimate our standard regression coefficients. The sampling variance of our ordinary least squares estimates are smaller relative to other ways we can do things. We can there are other ways of estimating regressions. There are other estimators we can use in regression that are also unbiased. But what we tend to see, so long as we're not violating assumptions, is OLS tends to be more efficient. It jumps around less. We got less variability in those estimates, which makes OLS a nice option unless there's some reason that we shouldn't be using it. Okay. People get this concept of efficiency. Okay. And then we also have consistency. Okay, consistency says that as our sample size increases, we start to become more confident that the value we're getting for our coefficient starts to become increasingly close to that actual population parameter. Okay, if I have an estimator that's not consistent, what that's saying is they might be unbiased, right? But what's happening is, it doesn't matter whether I have a sample of 50 or a sample of 300. My sample of 300 is no more or less precise than my sample of 50. I don't have a consistent estimator. Consistent estimators say that as my sample size gets larger and larger and larger and larger, I should get closer and closer and closer and closer to the population value with the estimate. Okay, so different ways of thinking about the methods that we're using to go through and get these statistics, thinking about unbiasedness, efficiency, and consistency. Unbiasedness, probably the most important one. But then we're also wanting to think about efficiency, how much of this does this jump around? How consistent, if I get a bigger, better sample, does it get closer and closer and closer? And so when we go through and think about in psychological science, we tend to just sort of go through and use OLS estimation. And that's fine because OLS estimation is really, really good under certain parameters. Those parameters are often things that we can meet, but we have other ways we can go through and estimate and run regressions with alternative estimators that maybe aren't sort of quite as great in some of these other areas. But if I've got data that are sort of horribly violating my assumptions, then maybe I need to switch to a different estimator. Okay. Characteristics of the analysis, sample data result in certain estimators being preferred to others, right? So for example, here, OLS is unbiased and consistent in collinearity, but it's no longer efficient. Okay, so the problem is if I have variables or predictors that are highly correlated, my estimates, all my coefficients here are still unbiased and they're still consistent. Like as my sample size gets larger and larger and larger, they're going to get closer and closer and closer to the true population value, but it's no longer efficient, right? What happens when I get high collinearity is I can get coefficients that start to jump around a whole lot, depending on sort of the specifics of the sample, right? And so I've got a problem with efficiency if I've got high levels of collinearity there. Okay. So just thinking about why screening is important to know sort of what are the characteristics of my data and what can I expect the impacts to be on sort of my estimates and how I go through and interpret that. Questions about this?
What was
Yeah.
the thing you were saying about if you had someone with 300 and someone with 50?
That's my consistency, right? What I would hope, Daniela, if I have a sample at 50 versus a sample at 300, I would hope that the sample at 300 is a better estimate of whatever I'm looking at than the sample at 50, right?
Okay.
If I don't have a consistent estimator, then that's not the case, right?
Gotcha.
So you can think about like, well, sweet, it doesn't matter if I have a sample of 50 or a sample of 300, that's like, none of that's good, right? We want, as our sample becomes more representative and sort of larger and larger, we're capturing more characteristics of the population. We want those estimates to become closer and closer to the population value.
And can you say one more example for efficiency? I was confused in those two.
Efficiency, this means that if I think about, so again, I'm measuring, yeah.
So when you were saying that, I was remembering your example at the beginning of last semester, like when you try to gauge like someone's weight by picking them up versus
Yeah.
putting them on a scale.
Yeah.
Could that be an efficiency?
Yeah, for sure, right? Like it's not like it's fine, but it's just gonna be more variable in terms
Yeah.
of things, right? So again, Danielle, let's say I'm looking at the relation of weight and height, right? And I've got a couple of different ways to calculate that correlation, right? And say I've got sample size of 100, 100. And I go through, and I'm getting random samples of 100 and then estimating the correlation between weight, the association of weight and height. And the association between weight and height has some population value, we don't know. But what we would say is that both of these, the two ways, method one, right, two, okay. One of these, I go through and I resample all possible samples of size 100 that I could from the university. And I find that my distribution of those coefficients looks something like this. And here's the mean. Here's my mean. Our weight, height is, and here's my population. Weight, height, okay. I'm saying, okay, here's what it is, but any of those samples can vary about, right? But let's say I have an estimator that's less efficient. Okay, what I might find here. Okay, so here. Right, still equal to these are the same value, it's still getting there. I've just got more variability in where those estimators land than what I've got here. Okay, and so what I would say, they're both unbiased, they're both getting at the same value, right? And the average of these across all these samples is still getting at the same value. The thing is, this is just a more efficient estimator than this because there's less variability. My estimates jump around less. Okay. And then the consistency is just saying as my sample size increases, I get closer and closer to this. Versus if I don't have a consistent estimator, it doesn't matter. If I have a consistent estimator, this is the distribution I would expect with a bigger sample than this with a smaller sample. If I don't have a consistent estimator, doesn't matter. If I have a sample of 50 or a sample of 500, this is still the distribution I get. I've got a problem with consistency there. But the reason this is all important is because depending on the characteristics of our data, that can start to fool with the properties of our estimator. To be aware of that. Okay. All right, so ordinary least squares, most common, right? What we're almost always trying to do in our regression model is minimize the squared residual for each observation, but other loss functions are available here. Ordinary least squares, we're looking at trying to minimize the function of the observed value relative to the mean of y, as opposed to the expected value of y, okay? So we're squaring that. Here, weighted least squares, we're adding some weights to each one of those individual things, and so there's some weighting strategies. Least absolute residuals, we're going through and we're looking at the absolute residuals instead of the squared residuals. So different ways of going through and doing this, but in general, OLS is gonna be our best bet and have the best properties, which is why it's kind of the default for most situations. But for example, if I have data with extreme heteroscedasticity, and we're going to talk about what that is, then weighted least squares might be a better option. Okay.
That was for increased through.
Yeah, if I've got a situation where I've got problems with heteroscedasticity in my data, weighted least squares is going to be probably a better option. Okay. But even though we do have alternatives, this is the other thing too, people over-identify a reason why they need to go do something fancy just so they can use something fancy. If you're gonna deviate from ordinary least squares, you wanna be able to justify that decision, make an argument for like, nope, this is what's going on in my data, this is why I've chosen something different. As opposed to just doing it because it seems cool, okay? All right. We're not gonna do much with different estimators, but just want you to be comfortable and kind of know what some of this stuff, where some of this stuff is coming from. Okay. All right. Let's jump over to. All right. So, gonna switch gears, start talking about some more practical stuff in terms of screening procedures. A lot of this is going to be review, because it's stuff that we've already gone through before. We've done a lot of screening of data. Just gonna go through, review that to make sure that we're all on the same page. As a couple of things Matt and I have discussed. It seems like people are still a little bit confused in terms about some screening stuff. We'll get squared away with that. Then we're going to talk into underlying assumptions of regression, and then we're getting into the new stuff, which is looking at screening observed variables and residuals within the context of regression. Okay. Please read chapter 4 of Tabachik and Fidel. Have good notes, have a good, like that will make your life exponentially easier as we're starting to get into regression, because this is going to get thick. There's a lot of concepts to keep track of. Make sure that you go through, read that, and take good notes there. Okay. All right. So Why worry about screening data, in the first place, okay? This is something that we kind of know we should do and sometimes don't do it. You know, people are like, well, it's fine. You know, it's kind of a thing that you should do, but like, I don't often do it, right? For the types of stuff that we were doing and training to do, and if we're gonna start reporting, research and trying to publish it, it's just responsible practice, okay? What we need to do is go through, if I'm saying, here's the analyses that I wanna do, I wanna make sure that the data that I'm using at least kind of approximates the underlying assumptions of the analysis I wanted to do. As soon as my data violate those assumptions, now all of a sudden I start to lose confidence in my estimates and my results, right? If everybody thinks I'm playing football with 11 people on a team, but actually what you don't know in the background, I actually have 14 people on the team. It changes the rules a little bit, right? And I'm less confident in sort of results at the outcome and things along these lines, okay? Same thing with our data analyses. So just being responsible, this is just an excellent reason to do things. But as an investigator and someone who conducts research, screening is a great way to just sort of really deep into your data and understand what's happening, okay? Anytime you go into a defense meeting or something along those lines, like you should know your data inside and out. Like any random question someone wants to come up, be like, oh yeah, no, that variable is kind of skewed, or we had some extreme values with that, or like actually we've got more variability in this than that. And what that does, if we start thinking about what that means, it starts to tell us a little bit more about the phenomena of interest and how we're measuring it. And does my design seem to be capturing the types of things in my sampling procedures working good, right? Like if I go through and I'm looking at social anxiety, and I go through and like, oh, here, I'm just going to use this measure of social anxiety. And I go through and I get screening data from our undergrads, and everybody's like in the 90th percentile of social anxiety. I should notice that and sort of maybe be concerned that my measurement tool isn't that great, that something's gone wrong, because that's not what this should look like if I'm actually getting at what I'm getting at, right? So again, thinking about the adequacy of your design, experimental folks, you know, maybe let's say that you're going through and you're looking at something and you got this slick design, right? You're like, okay, I'm going to randomize people to this group and that group, and we should be getting way different results in terms of scores from students based on whatever my manipulation is. And after you run maybe 10, 15 people, you're looking like everybody's scoring the exact same. Maybe telling me that what I'm doing isn't effective, or like I had a good idea, but the execution isn't great, something along those lines. Really nice way if you're going through and screening and sort of being careful and thinking about like, what does this actually mean? A great way to understand your data, okay? Then other thing too, thinking about informing the development of continued research, right? A lot of times, if you like me, had sort of what I thought was a pretty good idea for what my thesis was like. So we had a thesis, a third year research project and a dissertation. So we had 3 research projects at Buffalo. It's a different, wasn't a scientist practitioner model, right? But so I had my sort of third year project, which was pretty cool. But after I got finished up with it, I'm like, kind of missed the mark. There was some stuff that just didn't quite sort of connect, right? So thinking about like, okay, what did I do? What were the data I got? How do I tweak this to turn this into something that's useful? And then sort of like, what are the next steps? All right, well, I couldn't say this about this phenomena or these associations because I kind of didn't quite capture the thing that I wanted to capture. What are the data saying? How do I go through? What are some ideas to go through and fix this for the next study to make that improved and better and things along these lines, right? So thinking about what are the important next relevant questions, what are the limitations of existing ways of going through and trying to study these types of things, okay? You might go through, run your study and find, yeah, I've got, things were pretty good, but I got this whole collection of cases that the model doesn't work really well. They were all outlying values. They're weird kind of multivariate outliers and things like that. What's going on with these folks? Oh, these are actually a different population of people that something different is going on over here for these folks, right? I wonder what those folks are. I wonder what's happening. Hey, this is a cool idea. Someone ought to go through and look at this because this is something that things aren't working in this to like subset of the population. If I'm not screening my data and I'm just going through and throwing everything else, that's something I'm gonna miss, right? So there's cool stuff that you can go through and glean based on just working through your data screening stuff, okay? Now, in the extreme, what can happen is you can get very, very, very different and misleading results based on the data. So this is a famous kind of standard set of relation between two variables, X and Y, okay? But if you go through and statistically just look at this with our summary statistics, our regression lines and things along those lines, these are interchangeable data sets. They all give us the same mean, they all give us the same variance, they all give us the same regression coefficients here. But very, very, very different relations that are being captured here. This is perfect. This is what we want to see. This is our standard. Looks like X and Y are related in a linear fashion. Good. Okay. Haley, what's going on here?
Looks like you were starting to have start out as like a linear, or it was like a positive correlation, and then it kind of plateaued.
Yeah. So what's the actual association between X2 and Y2 here?
But it's pretty inconsistent.
What's that?
It's inconsistent.
Is
Like,
it inconsistent or is it perfect?
well, it's starting to decrease.
Yeah. If I go through and estimate this with a regression line, I'm like, yeah, X and Y are kind of related, but they're not perfectly related. Is that true? No, these are perfectly related. If I know what X is, I can perfectly predict what Y is. It's just not a linear function. It's a parabola, right? I've got a curvilinear function. And so if I just go through and I use a regression models can say like, oh, these two things are kind of related. No, they're not kind of related. They're perfectly related. It's just not following the linear relation. We plotted the wrong association between these two. And so we've underestimated the extent to which X and Y are related to one another, right? But if we don't screen, if we look at it, screen it, that's very obvious. But if we don't, then we're just like, okay, now we've got a good regression model sort of going forward when we've actually completely missed the actual relation between these two. Okay. What about here, Kate? What's going on with this panel?
It's pretty closely following the line until you get to like 13 on the X.
Yeah.
Um,
Here,
There's just something randomly happening.
Yeah,
around there.
right.
Not random necessarily, but there's something happening.
yeah, hard to know, right? But here's my regression line. It says this is the slope of that regression line. That's actually not right. Like this is the slope of the regression line. I just got a weird ass case up here that's driving everything off and it's pulling everything off base. Now this could be an incorrect data entry. It could be someone who's just not taking the thing seriously. I don't know, but that's something to go through and assess because it's completely changing the association, right? Same thing here. I don't know what's happening here. We've got everybody's a constant right here at 8 and sort of variability, and then we've got one case way out there that completely pulls this. Without this case, what's the relation between X and Y? It's nothing, right? It's a flat line. There's no, so X is actually a constant, which is problematic, right? But what we've got is one case out of this entire set, telling us that we have a relation between these two variables when we very clearly don't, right? So again, these are some kind of a classic, but what's interesting, I think, is if you go through these all produce identical regression lines and standard errors despite being very, very different sets of data, okay? So going through screening, doing the visual sort of inspection of stuff, all of that starts to become very important. Being able to describe data, what it looks like, so that we can go through and know what we're getting into before we start crunching out numbers and things.
So after we screen our data and we like figure out what's making its shape irregular, then we would most likely end up with like the first box.
Well, it kind of depends, right? Screening is the first step. We can have a game plan. Then we'll run our screening to see if the game plan is reasonable and then sort of make adjustments from there. Okay. All right. So again, just being familiar with your data is going to force you to have a deeper conceptualization of your research question, study design, constructs of interest. If we're thinking carefully about doing this, and again, like nothing I ask you to do is just to have you do it to do it. Because that's really takes me off. I feel like I got busy work to do things. I want you as you're going through thinking about like, what does this mean? What can I infer from these data? What inferences can I make and how is that going to inform my choices forward? Okay. So this is all super review stuff, right? Again, when we're going through regression, first thing we want to do, accuracy and plausibility, right? Are my data within expected range? Do my values all make sense, right? Are my variables coded appropriately? Am I sure I know what 0 means and what 1 means for dichotomous variables? Like, does all of this stuff make sense? Do I have my variables, are they appropriately labeled, right? Do I have the expected number of cases, right? So all of this stuff, making sure, do I have what I need to have in these data, okay? Again, you've gone through, this is not anything new, you've done this in every other set before. Going through just making sure that you know, looking at your categorical variables, your descriptives with your categorical and continuous variables, making sure everything sums up and makes sense given what things should look like. Also wanted to think about missing this, okay? Now we've gone through and done this before, going through and saying, hey, I've got this many missing values. One is sort of in our means-based analyses and our group-based analyses, making sure we're documenting what group those missing values are coming from. If I got a lot of missing values and all those missing values are coming from one group, that might sort of cue my interest in like what's going on with that group to maybe that might be influencing, hey, folks in this subset of the population or in this condition tend to sort of have missing values. Okay. What we're going to do with this semester is we start to get higher up into some regression and sort of more involved techniques. What we start to now think about is not only its level of missingness, but the pattern of missingness. Okay. And argument for the pattern of missingness is more important than the actual amount of missingness. Okay. If my missingness is happening at random, right? What we would typically think about at random, you can say that this is ignorable, right? I mean, it's not ignorable in that if I'm sort of missing like half my sample has missing data, and so it cuts my sample size in half, that's problematic, right? But if I've got a handful of cases or even a subset of cases, and it seems that there's no rhyme or reason, like if it really is random missingness, then I'm not biased in any way because it's just a random sampling of people who aren't included because they have missing data, right? But if I have non-random missingness, now that's impacting my inference, it's impacting my generalizability, right? Because I'm not capturing everybody, I'm only capturing a subset of people. There's a systematic subpopulation that's not being included in my analyses because they have missing data, and now that starts to become problematic. You've got a very great article assigned to this, sort of going through talking about how giving us language to talk about different characteristics of missingness. Okay. Now this starts to become less relevant it's relevant for regression models because we want to be able to sort of talk about the type of missingness we think is going on. And when we get into like SEM and stuff like that, where we have full information estimators that will go through and include cases with missing data. With regression, if you're missing variables of interest, then they just can't be in the model. Just exclude them. With full information estimators, they're still in there, but depending on the type of missingness, that starts to change, like whether or not we have confidence in the results that we're getting. If I have something that's missing completely at random, okay, what we're saying is that the probability of the presence or absence of a given value of my outcome is independent of all other variables in the set, including the value of the outcome. Okay. Basically, we're saying whether or not for any given case, whether or not a value is my outcome is present, has no relation to any of my predictors, and also has no relation to the actual value of y, right? So if I were to know what that individual's actual score was, that person's actual score has nothing to do with whether or not it's present or absent. Okay. Missing completely random is generally what we're thinking about when we talk about something as random is just like, yeah, it could be any sort of random case. It's not related to anything. Talking about this as MCAR. Missing at random. This is a little bit different. Here, the probability of the presence or absence of a given value is dependent on the observed values of X or some combination of X's, right? But it's unrelated to the actual value of Y after we control for the other predictors in the model, okay? Here, what we're saying is that whether or not I'm missing a value on the outcome, I can predict that whether or not I'm missing a value on the outcome based on something known about the scores on X or this combination of X's, right? So it's for sure not random. I can predict the likelihood or the probability of someone having a missing value or not based on my collection of X values. But once I account for those values, right, and once I account for those predictors, once I account for that, whether or not something is present or absent is now independent of the actual value of Y once I control for those other things, okay? In this case, I would say that these data are missing at random because my missingness is accounted for other things that I haven't, okay? So if I, and in the Switzer Roth paper, they talk about like measuring like blood pressure and things like that, right, in a doctor's office. If I'm missing blood pressure, variable values for some people, but I know that the people who I'm missing blood pressure for is based on previous assessment of blood pressure, and only people who have high levels of blood pressure are missing. But I've got blood pressure values from the previous time point. And I know that, yes, the reason that these values are missing is because they're higher or lower. And I have that data in the thing that I can predict who's missing. I know why they're missing. And so then I'm less worried about this. My data, even though we call it missing at random, MAR, it's not random like we typically think of random, but the missingness is accounted for in my set, right? I know it's why it's missing, and I've got sufficient values in here to predict and go through. We would still say that this is ignorable data within the context of a full information estimator. Our last option is missing not at random. We're saying the probability of the presence or absence of given value of Y is dependent on the true value of Y and then maybe on X's as well, right? So I've got some set of data where I'm systematically missing people who are high on neuroticism, but I don't have any other X value that would predict neuroticism. And so what I've got is non-random missingness where I'm systematically losing people with higher values. People with higher values of neuroticism are more likely to be missing data than people lower in neuroticism, but I don't have any way to account for that or predict that. I might suspect it, but I don't know. And so now all of a sudden I've got a missing not at random, and this is where we run into problems with stuff, okay? This is non-ignorable missingness. This is the stuff that starts to create biases in my estimates, things along those lines, yeah.
So if there were like, I don't know, previous literature that talked about how narcissism relates to missing info on the certain scale or whatever, would that move it to the like missing at random category
Yeah.
like they're previously known?
If I have something in my data set that accounts for that, right? Not just like I know why people are missing, but I've also have a variable that goes through and accounts for that. So I'll climb on my soapbox real quickly from a clinical standpoint. What happens when we use like SEMs and HLMs and things along those lines is when we're doing like clinical outcome data, right? And we're going through and we pull people in for treatment, and then we go through and give them treatment, and some people go through and complete, we have scores at the end, but then some people don't, right? And so with our SEMs, with our HLMs, things like that, we can go through and include everybody so long as we have initial data points for them, and those estimators account for sort of the missingness, which is a huge advantage of this type of analyses. Caveat is that those maximum likely estimators are predicated so that everything is assumed that data are either missing completely or random or missing at random, right? Do people drop out of treatment for random reasons? Nope, right? There's something about those folks that are going through, but what we're doing is we're pretending that the data is missing at random or that we have some thing that accounts for why people, are we very good at predicting who drops out of treatment? Nope, we're also not very good at that. Like that data is garbage. And it's a random smattering of looking at sex and ethnicity and sort of like different stuff that probably has nothing really to do, no consistent association on who stays in treatment or not, right? But what we end up doing is we go through with our big treatment studies and we just treat it as if it were missing completely at random when it's not, and we don't have anything in the data set that accounts for who stays in and who doesn't. And so what we're doing is we're estimating outcomes based on people who have completed treatment. We're probably systematically different than the people who don't complete treatment, but we're using data from the people who do complete treatment to kind of fill in the blanks for the people who don't complete treatment. When probably those people aren't representative of the people who didn't complete treatment in the first place, right? I don't know why people don't get more upset about this. It's a good kind of a situation, right? For experimental folks, if you were doing like EMA stuff on like I don't know, sort of beliefs about I don't know, sort of perspectives on the police or things along those lines, right? You're going through doing EMA stuff and following people along and getting perceptions and competence in sort of policing and things along those lines or something like that. But you found like what we're getting is those people who we suspect are maybe more impacted by some of these things or have certain political beliefs or something along those lines tend to fall off and we're not collected. They stop responding, but we don't have anything actually in the data set that goes through and accounts for, yeah, this is a thing, sort of the people who are losing are characterized by these things and we have those things included in the model to account for. Now all of a sudden you're making a bunch of inferences about attitudes based on people who aren't giving you attitudes that you're sort of in a completely, and so you've got kind of a different situation, right? So thinking about what the pattern of missingness is in our data, just because data is missingness is predictable doesn't mean it's problematic, so long as I've got a variable in there that accounts for why that's going on. If I've got something in there and I can model something that sort of predicts whether or not I'm present or absent, then I'm good. If I don't, now all of a sudden I'm sort of in this situation. I've got problems with generalizability. I've got problems with validity of my responses and things along those lines. Okay. Now I don't have a good solution for in the treatment case, like sort of just, I mean, we've got completer analyses, which are fine, right? But people get kind of sideways with that. I just want people to recognize that, yeah, like what we're doing is a huge violation of the underlying assumption of the model. Like it will give us an answer, but we should be very careful in our interpretations of what's going on with stuff. Okay, so
First two are ignorable and the last.
first two are ignorable. This not ignorable. Okay, so again, the batch I'll go through this, the switcher and raw. Go through. I've got a missing data worksheet. I'll go through and make sure I get that posted. It kind of summarizes some stuff. Important concept. We want to make sure that you have a good understanding of this stuff. Yeah.
I kind of have two questions. So, in like our problem set, do we report like which type of missingness we might be experiencing?
So for your problem set when you're doing screenings, you're still gonna just kind of go through and take a look, and you won't have enough information to know sort of what's predicting outcomes and what's not, and things along those lines. But if we are missing a lot of data, that's something that you should know in the problem set and sort of comment on it.
The other thing I was thinking about for like the missing at random, I was thinking about like COVID vaccine where people with like Pfizer had to take one, two, but then a lot of people missed
Yeah.
the second one. So let's say that there was a study, would you just get rid of the ones who never showed up for the second vaccine?
You could, right? Problem is that if those people who did not show up for the second vaccine are systematically different than everybody else, and I just eliminate them from my data set, I'm missing a subset of the population that needs to be represented in there, right? So you want to think carefully before you just like exclude people because of stuff, right? Other questions on this? All right, we'll talk about distributional assumptions of regression quickly, and then we'll go into break. So distributional assumptions, assuming multivariate normality, okay? Or excuse me, univariate normality. Scores for any one of our given variables, so long as it's not a dichotomous variable, follows something that at least kind of resembles, maybe even doesn't resemble, just doesn't deviate so far off a normal distribution to sort of be problematic. Okay, so like we did before, what we're going to do is for our continuous and our categorical predictors, we're going to go through and screen, look at distributions and things like that. But again, this is just the same stuff we've been doing before. NBD, not a big deal. What we got now here, though, when we start to get into multivariate statistics, is something what we think about is multivariate normality. Okay, multivariate normality says here that each variable and all possible linear combination of variables are normally distributed. Right now, here we're looking at joint distributions between combinations of variables. Okay, this multivariate normality is an extension of the bivariate normal distribution we talked about before with the correlations, right? Remember, we talked about marginal distributions, right? Which is just so the overall distribution of a variable. And then we talked about conditional distributions that says for a given value of X, Y has a normal distribution, right? So here, if we took cross sections of this, cross sections of this, that bivariate normal distribution, we have normal marginal distributions and then normal conditional distributions here with stuff. Okay, multivariate normality is like bivariate normality, but now we've added on not 2 variables, but 3 variables, 4 variables, and then we get into multidimensional space that's hard to wrap our heads around. Okay, multivariate normality is difficult to test directly. Okay, we've got some tests for multivariate normality, univariate normality. But there are problems. It's not straightforward, right? It's the same thing as if I go through and I calculate p-values for skew and kurtosis, and if you got large samples like I should have for regression-based models and things like that, p-values are going to be very small just because the p-value is testing whether or not something is exactly 0, right? My assumption isn't that it's exactly 0. It's just that it's not too far problematic, right? Now, luckily, a lot of our univariate and multivariate tests have been assumed to robust to violations of normality, right? Reasonably robust. We can have some weird stuff going on there, and it tends to be okay-ish, right? But this is starting to become increasingly called into question. Basically, someone told someone that it's fine, it's not a big deal if we violate normality assumptions, and then people went through and ran with that because it's kind of convenient to just say, oh, I've got a violation, technically it's not a big deal, I don't have to worry about it. That may be true, it may not be true. We need to be careful about this, which makes it very important that we're sort of going through, taking a look at our normality assumptions and being able to at least say, this is what our data are doing, here's the analysis I ran, sort of interpret that within the caveat that we've got some stuff going on. Okay. So again, always go through and make sure that we've got good tests on our assumptions. Okay. Multivariate normality assumptions is going to differ from grouped versus ungrouped analyses. Okay. For our ungrouped analyses, these are regression models and things along those lines. I'm going to assume multivariate normality if I meet 2 conditions. One, if each variable follows a symmetrical distribution, or it's kind of approximately normal-ish, and each bivariate relation is linear and homoscedastic. Okay, we're going to talk about homoscedasticity a little bit later on, but if I've got each variable in my set that included my regression model, if all my variables are relatively normal and all possible combinations, all bivariate relations are linear, so there's not weird nonlinearities going on, and their distribution of those are homoscedastic, which means they're sort of even, then we're going to say we're going to assume that we've met criteria for multivariate normality. Okay, so multivariate normality, hard to test directly, but we can go through, and if these 2 conditions are met, we can say probably close enough, we're probably okay and safe to go. Yeah. Now for group data, this is what we did all last semester, right? For our group-based analyses, our normality assumption now involves the distribution of sample means, not the actual variables, okay? So if I've got, Olivia, if I've got running a t-test, right? And I've got cell sizes, I've got groups of like size 50, and I've got, it's very clear that these, my outcome variables are not normal. Am I running out of the room with my hair on fire with that, or am I maybe okay? Maybe okay, right? Under what two conditions does the distribution of sample means start to become normal? Flashback, remember? Andy? If the population from which I'm drawing, whatever I'm measuring, if the population who I'm drawing from is normal, distribution of sample means will become normal very quickly, even if the data I'm looking at aren't perfect, right? What's the other condition? Sample size. We've got reasonably sized sample size, even if I'm pulling from something that is in the actual population has a kind of a skewed distribution or a non-normal distribution. We've got a reasonably sized sample. The distribution of sample means is going to turn normal very quickly, right? So here, with my group-based analysis, I'm less concerned about what my actual variables look like, and I'm more concerned about the sampling distribution, okay? My regression analyses, I start to become more concerned with what those actual data look like, because what it can do is it can start giving me weird residuals, and they can start to cause problems pretty quickly, okay? We're still screening for our group-based analysis because we want to be able to say what's going on, right? And if I have smaller cell sizes and I have extreme values that are quite extreme, and I'm worried about that dragging my mean around, then that's a problem, right? But we need to be more careful about thinking about what's going on with our regression models, and we'll see this if you get funky, if you have variables that have funky distributions, it starts to give you funky residuals, and it makes everything a whole lot more complicated. All right, cool. Let's go through and take a break. Let's be back at 3:40, and we'll get back on this stuff.
Oh.
Let's resume talking about stuff we've already talked about, and so hopefully will be an easy information to digest. Okay, thinking about if we're talking about univariate distribution, just the distribution of our variables, right? Or what we talked about previously in bivariate distribution, we talk about these as marginal distributions, the distribution of the whole variable. Talk about skew, okay, looking at the symmetry of our distributions. Positive skew, tail going to higher values, negative skew, tail going to negative values, right? Issue with our skewed distributions, we know the mean is always going to get pulled out to the tail. The mode is going to be somewhere on the other side. Median is going to be set up right in the middle, which is generally why we identify median as a sort of the preferred measure of central tendency for very skewed distributions. Okay. Luckily, the types of things we do in psychological sciences, we'll see skew, and sometimes it can be problematic, but a lot of times we just have artificial ceilings on how high our values can get for different things. But if you're thinking about, you never see mean income reported, right? Or mean house value, because the high end of that can get so far out, it starts screwing with stuff. And so this is why you'll see median values set up for these, okay? So again, the concern with skew that's very dramatic is that our mean is no longer our best index of central tendency, right? And everything's kind of getting pulled out. So one, go through, take a look, make sure that we're identifying problematic skew. Kurtosis, remember that this describes the shoulders of our distribution, okay? And the peak is the distribution. Positive kurtosis, we would technically identify this as leptokurtic. You don't need to sort of worry about that if you don't want to. Can if you're fancy. Here we've got sort of a very peaked distribution with some kind of flat tails, thick flat tails that are going out. Our negative kurtosis are platykurtic distributions. these have kind of a flat center, kind of heavy shoulders. Think about our square distributions as being sort of a good example of a negative kurtosis, right? Where I've got sort of values about this same number of values across all possible values, and everything's just kind of square. Okay. Problematic with the kurtotic distributions, they tend to underestimate population variance, cause biases in our standard errors or parameter estimates and things along those lines. Okay, so in terms of regression, going through and sort of with the stuff that we talked about before, what we want to do is qualify the magnitude of these things. It's not a yes or no. Is it problematic? Yes or no. It's a matter of degree. Okay. Indices for skew and kurtosis available. You've gone through, looked at all those things. Test of statistical significance is not useful. The test of statistical significance are just saying, do we have evidence that the skew or kurtosis value is not equal to 0? We're not concerned if it's exactly equal to 0, particularly if we have large samples. Anything that's trivially different than 0 will get flagged as significant, right? So we've got to be sort of have our head on the swivel, make sure we know what we're looking at with this. Okay. So what we're going to do is take a look at the shape of the distribution and absolute values of skew and kurtosis. Okay. Now, general guidelines and what we've used before is talking about skew and kurtosis less than 2 as a general guideline for deviations that are probably acceptable for the most part. Okay. What you don't want to do is say, oh, skew and kurtosis were less than 2, and so the data is normal. That's not the case. If I get a skew of 1.5, what does that data look like? Pretty obviously skewed, right? So it's sort of ridiculous to describe it as normal when it's clearly not, right? Well, what we can do is start saying things and being careful with our language and saying values of skew and kurtosis were generally acceptable within these data, right? And I'm sort of giving actual values, right? Now, Haley and I might have a disagreement on what's acceptable, but at least I've given you the information to say, this is what I'm calling acceptable, and then we can have a debate about that, right? Skew and kurtosis values fail to provide evidence for problematic deviations from normality, right? I'm not saying they're normal. I'm just saying they're not far enough from normal to make me super concerned, right? But again, have given the reader information to know kind of what's happening with this. Skew less than 2, kurtosis less than 8 could be interpreted as acceptable with reasonably large samples. There's a Klein SEM book that sort of is talking about that. Kurtosis of 8, that's pretty blocky, right? But if I've got a big enough sample, you know, if the main concern with kurtosis is not sort of fooling around with the sort of dragging the mean around, it's more about variability. But if I've got a whole bunch of people in my sample, I'm probably less worried about it, right? So again, if we look at Tabachika-Vidal, talking about the impact of kurtosis, saying positive kurtosis, right? That's going to be our skinny top and our flat tails, negligible for regression in most of our continuous models at about 100. Negative kurtosis, it's kind of blocky. Once we get in samples above 200, we probably don't need to worry about that too much, right? So again, just understanding that as we're going through and running through these, it all depends on context. It depends on the shape of our distribution. It depends on what we're measuring. It depends on how many people we have in our sample, right? So it's a complex, there's a number of decision points. We want to take this all into consideration as opposed to just saying anything like 2.1 means that I have a violation and 1.99 means I'm cool, right? Want to push you off of that sort of dichotomous thinking. Okay. Again, histograms also often a useful representation of our univariate normality, useful for identifying extreme values, right? Just know that those histograms, the drawback of histograms, they make a nice picture, but depending on how I set up my bins, I can get a very different looking picture relative to sort of what's going on. So just sort of keep that in mind, which is why I have you go through and also look at box plots. Box plots are the same no matter what across any program, because there are rules about what features, what corresponds to different features. Histograms are kind of a free for all. You just kind of make them look nice. So they're a good guideline, but want to use multiple pieces of information in determining our general distributions. Questions about this? Yes.
I do, so. The bullet point about like positive kurtosis negligible at n is, and if n is more than 100 versus negative kurtosis, so. Are you trying to say that like a good sweet spot would be in between for it to not be too negligible?
No, so if I've got positive kurtosis, but I've got a sample of over 100. To batch it, I'll say that's probably fine. You know, right? I start to get less concerned about this. We got negative kurtosis, come that boxy distribution. Got a sample over 200. It's probably, it's probably not something to get too worked up about.
Okay, so don't worry too much about them if it exceeds those values.
Honestly, large samples fix a whole lot of stuff. So, you know, if we don't have a silver bullet, but if you got a big enough sample, it just makes, I don't know. Money doesn't sort of create happiness, but it sure sort of like relieves a lot of stress every once in a while, right? So the same thing like that. If I've got currency in terms of sample size, it helps me sort of weather a lot of things that might otherwise sort of rise as problematic.
Thank you.
Yeah. All right. For our group-based analyses. Again, this is just going back through. This is just a straight refresher from last semester. Generally think about our group-based analysis as robust violations of normality, so long as I have reasonably large samples, right? The normality assumption is the distribution of sample means, not the actual observed means. And I know that if I've got reasonably large samples, I mean, there's some research that says as low as cell size of 25. I don't know if that would give me great levels of comfort, but as long as you've got reasonably decent sort of represented cells, again, that sampling the distribution of sample means is going to get pulled pretty quickly. So I'm less concerned, so long as I don't have sort of weird outliers that are going to drag my mean around, right? But again, remember that situations where I start doubling down on stuff, right? So if I've got distribution, if across my groups, I've got a different shape of a distribution and different variances. I've got a violation of homogeneity of variance. And in sort of group A, I've got a positive skew, and group B, I got a negative skew. I don't know, that's too much stuff going on. They're probably gonna have some problems here, okay? If I've got different sample sizes and different variants, right? Again, the sample with the more people is gonna have a more influence on sort of the overall estimate of my variability, right? So I've got a violation of homogeneity of variance. I've got a sample of 20 and a sample of 100. Now, if the larger sample has larger variance, the overall estimate, my mean squared and my ANOVA is going to be pulled towards the bigger sample. It's going to be my variance is going to be too high. I'm probably going to have too conservative a test because it's going to have a bigger estimate in my standard error, which is going to make my standard error bigger. It's going to make my test conservative. If the larger sample has smaller variance, mean squared error in my ANOVA table is going to be overly influenced by the larger group that has less variance. It's going to make my standard error smaller. It's going to inflate my test statistic, right? So again, making sure that we identify these things and the potential impact that they might have on our outcomes. Small sample sizes and violations of normality. Now all of a sudden that's a problem because things start getting jerked around, and so I don't have enough people in here to weather Mesa's score that's 7 standard deviations away from everybody else, and so I've only got 15 people in my sample, and so now the mean for the group looks much higher than it would be if Mesa hadn't been there, and now we've got problems like that. So again, having large samples sort of starts to help with this stuff, but also thinking about the balance of our design, differences in variability and things along those lines. All right. Outliers or extreme values. Okay. I like extreme values just because it seems like less of a categorical thing. But we can call these univariate outliers, we can call these outliers extreme values. Talking about a univariate outlier, this is an extreme value on a given variable. Okay. Multivariate outlier, though, this is something we're going to add in new. This is a new concept. This is going to be some sort of atypical configuration of scores. This is a collection of scores that's going to be strange for some reason. Okay, so let's say that I have I'm looking at a regression model. And I'm looking at age at 10 years, or excuse me, age, income, and sort of region of the country, okay? So if I have someone who's 10 years old, that's fine. That's not a univariate outlier because many people are 10, right? That's not a real weird observation. I have someone with making $130,000. That's fine, people. That's a nice income. So but it's going to be sort of not an unreasonable estimate, right? I could have someone coming from the rural South. That's fine. People live in the rural South. There's nothing weird about any of these observations in terms of this stuff, right? But then what if I add them all together, right? Now I've got a 10-year-old in the rural South with a documented income of $130,000. Now all of a sudden you've got something because you've got a configuration of scores that's weird, right? And it doesn't make sense given what's typical of the whole sample. And so what we've got is a collection of scores. We've got a multivariate outlier, right? Individually, there's nothing wrong with this, but if we put it all together, we've got a strange configuration of scores that can start to do weird things to our model, okay? So when we've got our outliers, different things, we always want to see if we identify an outlier, we want to start thinking about what's going on, like what's causing this. Could be incorrect data entry. This happens all the time, right? Always want to go through, make sure nothing's miskeyed. This is why it's always good to have original data sets, hard copies, so we can go through and say, we have an RA that messed up an entry, is there something going on, right? We can go through Bail and SPSS to specify a missing data code, right? A 999 variable, that's what I use to go through and indicate a missing value because there's nothing that I measured that actually where 999 is a real numeric value, right? So it's pretty easy, but if I forget to tell SPSS that that's a missing value code, I'll get a histogram that's got like everything here and then something way out here. I'm like, oh, whoops. Or a mean that doesn't make any sense or things along those lines. Looking at min-max values, I'm like, oh, whoops, need to go fix that. You can also have a case that's not an intended population, intended member of the population of study, right? So I mean, this is what is. I haven't changed this slide for a while in this example, right? Is we got the honeyboo thing going on here, right? If I'm interested in sort of the intersection of income and age and sort of things, this is maybe not someone I'm interested in just because they're such an atypical case. It's not a representative case of the group that I'm trying to contextualize. So I might say, gonna go ahead and get rid of that, right? Or if I'm going through and I'm looking at the income of undergraduates, right? And I go through and I see an undergraduate who's reporting an income of $150,000. I mean, oh, this is a non-traditional student who's like an engineer coming in to take a philosophy class just because they want to. Cool. Not someone I'm interested in sort of looking at and so getting rid of that person because they're not a member of the population I'm wanting to study. Okay. You can also have a situation where a case is an intended member of the population to study. The population is just variability is just underestimated by the sample. Okay. So I'm looking at so we're looking at Lindsay sort of eating stuff or things along those lines, and I come in and I'm looking and I have someone who is like a student athlete who's say 6'10" and 250 pounds or something like that. You're like, boy, I'm not worried about sort of eating behavior in those folks. It's just I don't have a big enough sample to capture many of those people on the tail. And so this is someone who's sitting quite a ways out from the rest of the distribution. Not that I'm not interested in them. My sample size of 50 just isn't big enough to capture the full variability. And so this person is very, very different than everybody else that I have in here, right? The answer to this is going to depend on like how I want to go through and address this, whether or not I smooth, whether or not I sort of keep this person in, keep this person out. There's no right or wrong answer. What you need to be able to do is identify why this person is strange, determine whether or not there's someone you want to or should have in your sample, and then what am I going to go through and do about this? Okay. So if I ignore it and just leave it in there, undue influence on my estimates, my coefficients, those go all over the place. Who knows what's gonna happen with that, right? Inflated type 1 errors, type 2 errors, reduced generalizability of my solution, like wild things can happen. Like I can't predict what this is gonna do to my model. But if I go through and I run these data with this person in and with this person out, and if my results start to jump around considerably, that's probably a consideration that I probably shouldn't have that person in my model if they're sort of dragging things around that much.
Did you say like if you keep them in and if you remove them?
Well, there are different ways of going through and thinking about doing this. So one thing, which I think is very smart in many ways, although there are arguments against it, is if I've got a person I'm worried about and I run my analysis with that person in, take a look at my results, and I run the analysis and leave that person out and see what happens. And if not much changes, then functionally, they're not having too much of an impact, even though they are kind of an extreme value. It looks like functionally they're not having much of an impact. And so then my default would probably just leave them in so that I don't have to explain why I kicked somebody out. Anytime I kick someone out for not doing what they're supposed to do, it makes it feel like I got my thumb on the scale a little bit. So I want to give a good explanation for why I removed somebody, right? Now, if I go through and I have somebody in there, I get one set of results and I pull them out and I get a completely different set of results. That says that one person in my sample is having a massive impact on the overall picture and things like that, which suggests that that's maybe not a good idea to have them in there, right? Now, the problem is that maybe when I have them in there, I get an outcome that's more favorable to what I want. If I pull them out, then everything starts to fall apart. Now I'm in a predicament where maybe I'm tempted, the devil on my shoulder, to keep them in because I get better results or things that look better for me if that person is in there. But I know if I pull them out, everything comes crashing down. And this is so the argument against sort of doing this, sort of looking and running your analysis with and without, is that it puts you in a position to maybe make decisions that are more serving to you than help generalize results to sort of everything, right? But I don't know. I think there's probably a middle ground to be had there. So, but anytime I have, particularly if I've got a reasonably large sample, if one or two people completely change the whole pattern of results, probably means that those people probably shouldn't be in there, because if I got a decently sized sample, one or two people shouldn't completely change the whole picture. So, in terms of identifying univariate outliers, okay, this is the thing we often forget about. And this is going to some group-based analyses, but also for our categorical or for our continuous models where we've got dichotomous indicators, right? If I have dichotomous variables with uneven splits, 9-to-1, we can still talk about these as outliers. So we don't think about dichotomous variables as having sort of a distribution necessarily, a normal distribution. But if I've got hugely unbalanced groups where it's again like a 9-to-1 situation, what ends up happening is any individual in that smaller set is having a much bigger impact on the overall outcome relative to any one individual in the bigger set, right? So again, in Wyoming, if we're doing this, this often comes in with, I'm looking at underrepresented groups versus sort of majority white participants or something like that, right? I might not be able to capture much. Now all of a sudden I've got maybe this is a terrible way to code it, but like a sort of a underrepresented group versus everybody else, right? If there's a question that would make sense to go through and look at it that way. What happens is any sort of individual within sort of my underrepresented group has much more influence because there's only a handful of them relative to the one person in the sea of white people that we have in the other group, right? And so now all of a sudden we've got a problem where any individual case starts to have a bigger influence with that smaller group. What we can do is we can, when we have that much of an unbalance, we get it starts to distort associations. We'll typically tend to attenuate it. So if we have an association between a group and variable and something else, it doesn't look as strong as it probably should. And so again, unless we've got something that's really critical to our analyses, might want to consider leaving that out because the inclusion is maybe gonna have a more detrimental impact than having it in. Now, if you're going to do research where you want to get sort of smaller, let's say I'm like, oh, I want to go through and take a look at sort of this stuff, but I also want to look at whether or not PTSD has an impact, right? So I would hope that not very many people in my sample have diagnosable PTSD. And so maybe it's like I've got 90 people who do and 7 who don't, or excuse me, 90 people who don't and 7 who do. If this is just kind of very variable, I'm just kind of interested in, it is not critical to what I'm doing, I'll probably just leave that out, just because I don't have enough representation there to include it. If PTSD diagnostic status is something that's really important to my study, I need to plan on that ahead of time and make sure I'm oversampling to get enough representation in that group so I don't run into a situation where I've got a univariate outlier on that dichotomous grouping variable. Okay. Questions about this? Okay. Continuous outliers, this is where things start to come in where like, oh, okay, stuff that we've done before. Now, want to get some clarity. So Matt and I both noticed on sort of this, a lack of sort of maybe standardization in terms of identifying what constitutes an extreme value in a continuous distribution. Generally, we're using our z-scores for this, right? If I find a z-score 3.29, 3.3 is that marker where we would have p less than 0.00, p equal to 0.001. We're saying that we've got 3.3 standard deviations away from the mean. That's capturing, less than 0.1% out there in either tail. We could probably identify those as pretty large values. Now, if I've got a smaller set, maybe I sort of go through, but like usually around that 3 value, what people have tended to do in their screenings is identify like z values of like 1 and 2 and stuff like that as extreme values. Those aren't extreme values. Those are sort of just, if there's a set that, if there's a score that kind of sets away from the rest of the distribution, you can identify that in the histogram. Just not wanting to over-identify what we're calling outliers extreme values with this stuff. Yeah.
I know we don't do like the black and white rules, but are we like really specifically looking for like 3.29 or greater, or like if we saw 3, should we be concerned about that comment?
So it's all kind of relative and looking at that distribution and sort of a combination of things, right? If I'm just left looking at like a list of z-scores, I'm having a hard time knowing like, is this bad? Is it not? Right. And so, but when we combine that with our histograms and our box plots, we're like, okay, well, we've got some scores that are out there on the highlight. So anything that it's above this is probably worth kind of mentioning. But then if we got something that's real far out there, or maybe we got something that's like 3.2, but everything else is kind of stacked up. And then we got this case that's really kind of hanging out there, might be worth going through and mentioning. Right. So again, when you're going through and running your screening, you should be thinking, you put yourself in the standpoint of consultant, right? Someone's giving you a bunch of data and like, hey, what's going on with this, right? You're sitting down and be like, hey, here's some stuff that's going on, things that are fine, right? If things are kind of a continuous part of the distribution, you got z-scores that are sort of 3-ish or less or things along those lines, are probably not worth sort of reporting or worrying about things like that. But if you do have things that are cases that are sort of starting to get far away and sort of sitting, getting far out there, want to say, all right, it's this case, this is the actual raw value that they're reporting on this variable. This is the standardized score that we're getting for that. So this is sort of a case that's kind of looking like it's a little bit higher. Okay. So now note that if I've got a very, very large sample, if I've got a sample of 200, 300, something like that. I mean, that's not very, very large, but it's a decent sized sample, right? Probably I'm going to catch some people on the edges, right? Which is kind of the whole point of what we're trying to do with those, is get those extreme values. And so if I've got a big sample, I'm probably going to get some large Z values. That doesn't mean I need to freak out. I should probably identify them, right? Like, hey, here's some people who are scoring very, very low. Here's some people who are scoring very, very high. Just to let you know, these folks are in there. We're probably not worried about them because we've got a pretty big sample. They're kind of just hanging out in the tails. They're not going to screw with anything, but these are cases that tend to have higher scores. And then when we get into some of the regression diagnostics, those are often the cases. What we're going to be doing is we're looking for repeat offenders. We're looking for frequent flyers. We're looking for cases that keep popping up again and again and again and again and again. And those are the cases that at the end of the day, we might get back. Does it make sense to have this person in there? Like if I'm weird on one day, that's fine. If I'm weird on every day, now all of a sudden we start to become more concerned about sort of what's happening, what's going on with me. Same thing with these cases, okay? Also going through and looking at the box plots. I think this is maybe where people are getting up. Matt, I don't know if this is, so your read as well, that maybe people are looking at box plots and identifying any case that's more than 1.5 times the interquartile range from and identifying those as extreme values. Again, don't do that. Sort of pull things together. So want to go through and sort of pulling information together to say, hey, yeah, no, this actually does look like it's a value that is notable for being quite high or quite large or quite small. But not just identifying anything that's sort of coming up onto these box plots as an extreme value. Okay. But here, just as a refresh, our box plots. These are just our midline. It's going to be our median, our bounds of the box, right? This is our first and our third quartile, right? This is the 25th percentile, the 75th percentile, kind of boxing in the interquartile range. This is the middle 50. 50% of my scores are falling by definition between those two. Okay. My whiskers, two things, right? These are good, sort of throw people for a loop. My whiskers can either be the minimum and maximum values in my data, or the most extreme values that still fall within 1.5 times the interquartile range from the median. Okay. Our extreme values are indicated by points extended beyond the whiskers. So these will be little dots in SPSS. If I get beyond 3 times the interquartile range, then I'll note those with an asterisk. Okay. But note that your box plot is giving you just a little bit different look on your data than your z-values. Z-values, these are mean-based statistics, right? It's how many standard deviations from the mean does this fall. These are all median-based statistics, right? And you can say, okay, these are values that are falling above and beyond, things along those lines. But we want to go through and to identify, being careful in terms of what we're flagging as notable or problematic values based on the combination of information. Okay. All right. So addressing our univariate outliers. Check the accuracy of your entry. There's an inaccurate entry, fix it, right? Another thing we might want to do is consider the possibility that I have a problematic variable, right? I went through, included a variable in my study, like, oh, this would be kind of cool. Gabe throws this in. He's like, oh, this will be cool to take a look at. But when he actually goes through and screens his data, like the variable that would be cool to look at is maybe on like a kind of a weird scale that doesn't have a lot of psychometric evidence for it. But you thought, oh, maybe we'll collect this. It might be cool, but it's got a crazy ass skew. And looking back through the hard copies, it looks like maybe people didn't understand what they were supposed to be answering and things along those lines. And I've got but I'm finding that I have a lot of extreme values on that variable. Maybe cut your losses and just get rid of that if it's not something that's sort of intensely relevant to your research question. Okay. Think about whether or not your cases, any sort of case that you're finding is representative of your population of interest. If it's not, you're like, oh, whoops, I caught this person. Cool for them, not someone I'm interested in. Go through and pitch this person. Fine, you're not losing any generalizability because you're not trying to generalize that group anyway. Okay. Smoothing procedures, we talked about this. If it is someone who I want to keep in the data set, but they do have a value that it starts to become problematic because it's kind of out there. What we can do is smooth, right? Here we're bringing this person in terms of rank. They're still the highest sort of ranking person in the set, but what I'm doing is I'm just reassigning them a value to 1 unit higher than the next highest value in the set. Okay, so we're playing with the data here a little bit. I still want this person to be represented as the highest scoring person in my set. I'm just going to kind of bring them in a little bit so that they're not causing the problems. Okay, and this is a fine thing to do, so long as you're keeping track of who you're doing this to and making sure that you're being explicit and reporting to people that, hey, these are cases that I had to smooth because they had some pretty far outlying values with stuff. Okay. So Mesa, let's say that you're looking at aggression in kids with ADHD or something like that. And so for the most part, not too bad. You just got a kid that's out there in the playground that's just super, and I flagged them for a whole bunch of stuff, right? Maybe I don't want to throw that kid out because they're for sure someone I want to have represented in there, but their level of aggression is so high that it's going to throw everything off. Maybe I go through and just decide to smooth that and bring that value in. Everybody else is looking fine. The distribution as a whole isn't bad, but it's just this one case that's going to be problematic. Maybe I bring that in to smooth that a little bit. Okay.
That's not like making data that we want to see. That feels
Yeah,
real
no, it so very
real.
much is making data that we want to see. But the argument is what we're doing is we're still keeping that person at their rank as the highest person in the set. But to leave them in with an uncorrected value is going to throw our model way off base. And so what we would do, we don't want to exclude them. We want to keep them in there. But if everything else is looking kind of normal and fine, and then we've got one thing that's way out there, we're just bringing that person in to, and we would just call this a smoothing procedure. It's pretty common in terms of some ways to go. Okay.
So we just report that, like, oh, we had a smoothing procedure.
Yep, smoothing procedure for cases that are extreme value. And so what we did is go through and pull that person in.
It doesn't look bad.
Well, it's just so long as you're doing it. Because the other thing is not doing it and then having your results be horribly biased by one person. And so now it makes it look like everybody's like sort of wild with aggression and taking heads, right? When it's just one kid who's out there causing problems, right? So bring it in. Yeah.
Is there a specific way to do it that won't like pull it too much in the way we want? Like, obviously, if you're going from like a 20 to a 10, that's like a way bigger difference.
Yeah.
Going from a 20 to a 15.
Yeah, and so this starts to become, because what will often happen is that oftentimes, what this will do is it's actually, it's a lot of times it's not helping you. Because if you got one person who's way out, I mean, well, it's always helping you, right? The problem is if I've got a set of data. I got a set of scores here. Like that, right? What's my line look like here? Kind of something like that, right? And I got some joker way out there. What does that do to the strength of my line? That makes that very strong, right? Here, it's kind of sort of like, oh, we're kind of estimating, but now if I've got to account for that point, what this will often do, we'll talk about this as an influence point, it actually makes that association much stronger than it would be without that, right? And so by bringing that person in, we're bringing this person in and now maybe we get them to here. Now all of a sudden we've got something that's probably still reflecting sort of the overall thing, but it's less of an issue. So bringing that person in is probably, you're talking about making it look more like what I want it to. It kind of depends on what the functional impact of that is on my regression line, right? So it's not always like me doing myself a favor. It's just, I've got a case and I want to make sure it's represented in there. I'm just trying to pull it in a way that's, I can still go through and do so it doesn't screw my model over. Yeah.
If you have a big enough of a sample, would it be easier to just remove that one score?
If you have a big enough, yeah, you could just say like,
Okay.
boy, this person is just so extreme, it's just causing problems. And if this was a case that was causing problems across a number of different components, right, then maybe you go through and do it. But again, right, so in clinical, if we're going through like, there are some very severe people out there, right? And we want to make sure that we're not just accounting for people who kind of have symptoms, right? So it's a decision. You want to go through and think about like, what are my options? What are pros and cons? And then make a decision based on that.
I never make
Okay,
Is it? Like, based on your graph, it looks like you did it to both variables, like
yeah,
bringing both, is that like more common or like?
well, so what we would do is we would go through and take a look at sort of where that person, yeah, in that case, it sort of looks at as on both ends, and we'll talk about these as leverages and influence points and things along those lines. Would want to take a look and see who is this person, right? And so here, if I go through and I'm going through my variables and I've flagged this person as an extreme value of X, I've also identified this as an extreme value on Y and X2, X3, X4. That's when we start to think about like, is this someone who we want to have in our sample? What's going on? Was this person just like sort of peeking out, just like, I would want to go through and look if this is questionnaire stuff. I would want to go through and see how they were responding. Did this person just like, just circle the highest value on everything? If there's invariant responding, then I'm like, is this a reliable report? Is the score I'm getting for this person an actual good, valid assessment of whatever phenomenon I'm trying to measure? Lots of things to go back to and take a look at this stuff. Okay, so we can do this smoothing procedure. Typically what we'll do with the smoothing procedure, if I've got a distribution that's looking pretty acceptable, and then what will more often happen is if I've got maybe 2 or 3 cases that are way out there, maybe that smoothing procedure is me bringing all 3 of them in to where we've got, so the lowest one is the next highest, next highest, next highest, kind of line these up. And if I go through, bring those in, then my data is fine. Then the overall distribution is okay, right? But other thing that can happen, if I have univariate outliers, if I've got a table that just really goes through and stretches out, and so there's not 1 or 2 or 3 or a handful of cases I can smooth. It's a whole set that just continues to go through and spread out. This is now what I'm maybe thinking about. So do I need to go through and institute some sort of transform of these data? Okay. And what we're doing here is we're taking these values and we're creating some nonlinear transform of those values to kind of bring them in and get a better distribution.
Does that apply to the whole data set then, not just those that are?
Yeah,
all spread
that's the
out?
whole variable. Smoothing, I still have my raw variable, I just pulled in some scores. Transform, now I have a completely different variable and I have to deal with that, okay? Now, note that before you go through and sort of start moving through additional screening procedures, if you got univariate outliers, address the univariate outliers before. Like, so I'm going through, I've done my screening. I don't just be like, oh yeah, my distribution is jacked, let me continue on to go through and look at stuff. Because if you do, then everything else after that is gonna be all messed up for this reason, right? So in your screening procedure, if you find you've got problematic distributions, you need to hit pause, figure out a strategy for addressing your distribution. Make sure that that's looking good and then continue on, because when you start looking at bivariate associations and things along those lines, all that's gonna be messed up too, right? So always want to make sure your univariate distributions are okay before you move forward, because remember our assumption of multivariate normality is that all our univariate distributions are normal and all combinations of bivariate relations are linear and heteroscedastic. We need to address this first, because otherwise then everything else will just be ruined if you don't address it first. All right, so thinking about transformations, right? Like people get really overly excited about transformations, want to pull the trigger on transformations probably more often than they should. Want to think about the difference between here data-driven versus theory-driven analyses, okay? The drawback to transformation is it complicates our interpretations, okay? If I am talking about the relation between X and Y, and the relation between X and the log of Y, those aren't the same thing. Those are different variables that I'm going through and taking a look at. And I need to be able to, I'm prepared to recognize that I'm not just looking at the relation between these 2 variables. I've got the relation of maybe one variable and a nonlinear transform of another variable. A lot of times the nonlinear transform of that other variable doesn't make any sort of conceptual sense to me. It doesn't have any actually real meaning to me. And so it's fine, I can model a relation between X and the square root transform of Y. But if I don't know what the square root transform of Y means, then that starts to impact sort of what I'm actually saying and modeling and stuff, right? Now, transformation, sometimes necessary, and in some areas it's going to be common practice, right? If I'm an experimental person, I'm interested in things like, if I'm a cognitive psychologist, I'm interested in like reaction time. Reaction time is never skewed. It's always going to be skewed because there's kind of a lower limit for how fast I can respond, but I can sort of screw around and sort of take a long time. So that's always going to be skewed data set. And so if I'm doing reaction time data, if I were to report an analysis of reaction time data that wasn't transformed, people in my field are probably going to be upset about that because this is just data that needs some sort of transform, right? Same thing, clinical alcohol substance use tends to be highly skewed, right? And so the log transform of drinking occasions or something like that, it's not really something that's weird. It's just the variable that we use. And so people within that field might have a very good understanding of what sort of those values mean, right? But what happens a lot of times, I see this all the time reviewing papers, people transform just based on because I don't know why, but people just get really excited about doing this, right? We had significant skew. And if I read that, I mean, like, well, I mean, do you mean that you ran a significant test on skew and it just said your skew wasn't zero, so you went through and jacked around all your variables and made it a whole lot harder to understand what you're doing? Or do you mean significant as in like a substantial skew that required to be addressed, right? And so probably they don't sort of know. If you look at PSYC and Fidel, pretty liberal in terms of like saying, oh yeah, so go through and take a look at this. I'm much more hesitant with this because again, like I think being able to interpret what we're doing is so important. And so certainly if you've got a case where the transformation is appropriate and there's not another good solution for going through and doing this, then by all means transform, just have a good reason for it to be able to say, here are my options. None of these other ones seem to be as good. And so as a consequence, I decided to elect to transform. Here are the consequences. And so now the rest of my analyses and my interpretations are shaped around reporting a transform variable. What happens, people go through transform and then pretend that they didn't transform. They talk about the relation between X and Y. But you're not talking about the X and Y, the relation between X and Y, and where you're talking about the relation between X, some transform variable Y that I don't know what that means or has any conceptual meaning to it. So there are certain transforms that are easy to interpret and so other transforms that are less easy to interpret. So there's certain things that we can go through and pick up. We just want to make sure that if we go through and pull the trigger on this, that we're accounting for it in our interpretations. Okay. So in terms of common transformations, and there's whole sort of fields of statistics where they get into sort of really sort of intense, sort of involved sort of transformations and things like that. We see that less common in behavioral sciences. Some common ones that you'll see, if we have moderate positive skew, take the square root of X. So if we just have all of my values, I just take the square root of X, that will make a moderate positive skew better. Okay. Large positive skew, the natural log of X. Okay. I use the natural log, or I would recommend the use of natural log versus the log. It's not going to change the shape at all, but the natural log sort of has some interpretive properties that are kind of advantageous. And so we've got that. If I've got a large positive skew with 0 values, we've got the natural log of your value plus some constant, right? I can't take the log of 0 because it's undefined. Like it's like trying to divide by 0. You can't get anything. So if you do this, you'll just end up with a bunch of missing values. But if I go through, if I've got 0 values in my data set, and I go through and I just add a constant here and just add 1 to all the values, then it just increases everything by a value of 1, and then I can take the natural log of that and won't have any problems. Okay. If I've got a severe positive skew, I can take the inverse of X. So this is just 1 divided by X. That'll fix a very severe skew. Okay. With this, the thing to remember is that if I take the inverse of X, that's going to flip around my stuff. So if I have a value of 10, I take 1 divided by 10, I get 0.1. value of 1, I take 1 divided by 1, I've got 1. So what that does is it swaps around my scaling, so now large values are small and small values are large. If I don't keep track of what I'm doing, I'm gonna be reporting associations that are in the opposite direction of conceptually what's happening. So needing to take that into consideration. If I've got large L-shaped distribution with 0 values, now I gotta go through and add that constant, right? So I'm not trying to divide anything by 0, because that's not gonna work. We got a moderate negative skew, okay? Everything we're doing in terms of your skew is assuming you got a positive skew. If you got a negative skew, you need to go through and we need to go and transpose this set so that big is small and small is big. If I have a negative skew and I try and log transform it, it's gonna make my distribution worse. So what I first need to do is take the square root of some constant minus the actual value. K, this is just a constant subtracted from each score that the smallest value is 1. So typically we're gonna set K equal to the largest score in the distribution plus 1, and we're just reflecting that around, okay? So if my scale runs 0 to 100 and I've got a negative skew, what I'm gonna go through is I'm gonna add, I'm gonna take 101 minus all the values, and that's gonna swim things around. So the value of 100 is now gonna be 1, the value of 1 is now gonna be 100, it's gonna just like flop the whole thing around to give you now a positive skew that we can address with a square root or natural log or sort of an inverse, okay? So someone will do this, they'll have a negative skew, they'll try and put a transform on it, and it'll make their stuff way, way worse, okay? It's because we need to go through and flop that. We need to reflect that variable, flop it around, so we now have a positive skew, then correct that. But if we go through and we reflect that, what's happening is down is up and up is down, and we need to recognize what we've done before we then go through and change it. So you can start to see the conceptual and the interpretive gymnastics that go into this stuff. So mathematically, fine, I can take this variable and change it into something that sort of is more amenable to the types of things I want to do. I just need to make sure that I know what I'm doing and account for it in my interpretations. Again, I've reviewed papers where they went through and did some crazy ass transforming or reporting that, and then against all interpretations, what we actually found was that this was related to this in a positive direction, right? Yeah, because you transform this all around, so now down is up and up is down, and so it's not different. You just forgot that you did this, and now everything seems counterintuitive because you just swapped your scale around, right? So always want to make sure that you know what's going on with your data when you do this type of stuff. Okay. Questions on some of these common transforms? All right. Now, how do we go through and interpret our transform data? Okay. Now, if we're using our ungrouped analyses, right, so our regressions and things like that, we're interpreting our observed relations as associations with the transform variable. Okay. So we're saying this is the association of extroversion with the log of regression scores. Now, if you don't know what the log of regression scores are, I'm sorry, but that's the measure that we went through and sort of looked at, right? And so making very clear that we're explicit about that, so as we're not misleading. We can't just sort of execute a transformation and then pretend that we didn't, right? Now with group-based data, what ends up happening is interesting is anytime I go through and I'm looking at group-based differences on a transform score, essentially what I'm doing is I'm looking at differences in medians as opposed to means, okay? Transform changes the shape of the distribution, but not the order of scores, okay? If we measure you all on something, starting with Mesa, moving around, and ending with Mandy, right? And I've got you in, you just happen to sit in increasing disorder where you're increasing order, where every observation is increased by 1. It's just crazy skewed, right? If we went through and transformed that, your order in that distribution, your relative order in that distribution is all going to be the same. We're just sort of kind of pulling in and shrinking kind of what that distribution looks like, okay? So what we see is the cases that the median of the untransformed variable are still going to be at the median of the transformed variable. So if I go through and I take a look at, here's my untransformed data, right? I've got pretty severe skew here, right? I go through, transform my data, it just kind of goes through and reshuffles these, right? And gives me something that's kind of a nicer distribution to work with. But the median value of this distribution is going to be equal to the median value of this distribution here. The order doesn't change, it just changes the shape. Other things that you keep in mind is anytime we're talking about an association with a transform variable, what we're talking about is what we're essentially modeling is a nonlinear association. Okay, so here I've got X and Y, right? And we've got a curvilinear function here, looks like maybe a quadratic or something along those lines, right? And if I go through and I screen that and I take a look, I say, okay, well, what I've got is that X and Y actually have a very, very tight, perfect association here. But if I go through and estimate this association with a linear function, what's going to happen?
Strong.
What's that?
It won't show a strong
It
relationship.
won't show a strong, it'll show a decent association. Like, yep, X is associated with Y, but I'm going to be trying to fit a linear function to something that's not linear. And so it's going to underestimate the association between those things. So what I can do is I can go through and look at the relation of X with the square root of Y, right? Now I've got the association of X with the transform of Y. And now, Abby, what does that linear relation look like?
It's a lot stronger.
Right, so my square root transform of Y does a nice job of taking Y and turning it into something that holds a better linear relation with X. But what I'm actually talking about is I'm modeling a nonlinear relation, like X and Y hold a nonlinear association. By definition, we're talking about nonlinear associations if I'm running a transform. What I'm just doing is I'm just mathematically tweaking the values on that variable to make it fit a linear model better than the raw data. Okay, so really, really important and something that's cool, and I don't know why we don't sort of make a bigger deal about this. Essentially what we're saying is we've gone through and transformed a variable, we're saying that like I have a nonlinear relation between these two variables, right? I can make that relation linear if I transform this variable using this sort of transformation. But essentially what I'm looking at is like X is not related to Y in a linear fashion, right? Here, what I'm saying, the linear relation between X and Y is quite minimal until we get to a certain point, and then it picks up, and then we've got an acceleration function where it starts to get sort of steeper and steeper. That seems like kind of a cool way to understand these two relations, right? And sort of how these variables relate to one another. But if I just go through and slap a transform on it and say, hey, here's the coefficient, I kind of miss phenomenologically what's happening with this, right? So always, again, I'm become more open to transforms. I have in the past. I think it's a good tool. I don't think we should just do it for no reason at all. But if we do it, should we think very carefully about what that means between in terms of the association between our variables. Okay. Questions about this? Cool. All right. Multivariate outliers. All right. There's a couple of different ways to start to quantify sort of the magnitude of multivariate outliers. Okay. One way to think about this is in terms of leverage values. Leverage refers to the distance of a case from the centroid of the remaining sample. Okay, and the centroid is just the intersection of all means, of all the means for all predictors in an analysis. Okay, so if I say, hold up here like this, everybody is up X, Y. We got an XY axis, right? We've got X, we've got Y. And we can point to sort of something on XY space, okay? Do this, throw out that middle finger like that at a right angle, okay? Now what we've got, a three-dimensional space here, right? So here, I've got an X and a Y, I've got a bivariate regression. If I throw out another axis, now I've got three-dimensional space and I've got something hanging out here, right? So think about your leverage in your centroid. If I've got X and Y, and I say, all right, here's the mean of X, the mean of Y. This is the intersection of those two variables. If I throw out a third dimension, now my centroid exists out here in 3-dimensional space somewhere. And now if I add another predictor, now we're in 4th-dimensional space and 5th-dimensional space, and then it gets hard to sort of conceptualize and think about. But this is essentially what we're talking about in terms of your centroid. And then where does my case fall? I gotta talk, that doesn't work. Where does my case fall? Here's the intersection of all possible means, right? Where does my case fall and how far away is that from? If it's something way out here, then I've got a difference. So we just have to sort of transition into 3-dimensional space to start thinking about a simple case with 2 predictors and an outcome. And we get more predictors, then it gets harder to think about it, or at least for me, yeah.
Is leverage different than, I don't know how to say it, like Mahalanobis distance?
Yeah, we're gonna go through and talk about sort of, Mahalanobis distance is a version of leverage. And so we'll talk about different ways of going through and representing those. So here, if we go through and we take a look at, and again, just in the 2 variable case, we're looking at the relation of weight and height, right? We go through and take the mean of height, mean of weight in our sample. This is our centroid, right? And so here we've got a multivariate outlier because it's there's quite a bit of a distance. We've got someone who is heavier, who's on the shorter end. And so now all of a sudden, we've got something that's different in multivariate space from where we're at here. Okay, so case 237, we've got height 60, weight 220. We got to identify this as a multivariate outlier because these 2, the combination of these 2 things, this height, this weight, not necessarily sort of extreme, but the combination of those 2 together make that an extreme case. Okay. What if we add a third variable? Let's say we've got someone who's 76 inches tall. So we got someone who's 6'4", 230 pounds, right? What if we throw in a third, like what do we throw in as a sex variable that makes that all of a sudden something that's sort of notable in multivariate space? Yeah. If we put in someone who's just a woman who's there, just men tend to be very, like, for men, this is a large man. But if we go through a large person, but maybe not someone who's like way out of bounds, right? But for a woman to be 6'4" at 230, we're probably have pulled someone from sort of athletics or something like that, right? And so within the context of our space is going to be someone who's, and so just a way to go through and think about, we can have combinations of variables are just fine until we throw in a third one. And now all of a sudden we've got a case that's very unique for the specific configuration of variables. Okay. This was me when I used to weigh 230 pounds. Which is not the case. Describing our multivariate outliers, okay? Leverages other indicators is going to help us identify which cases are statistically kind of unique, but it doesn't tell us why they are, okay? What we need to do anytime we identify a multivariate outlier, our job is to go through and try and figure out what specific combination of variables is making this a unique case, okay? It's going to help us, doing this is going to help us identify variables that are problematic. Because if I have a bunch of cases that have come up as multivariate outliers, and it's all because people are registering high or low on some individual variable, it might tell me that there's something wrong with that variable. I need to take a look and try and understand what's happening. Helps me make a decision on whether or not this individual is part of the population I'm trying to generalize my model to. And if it's not, then I'm fine getting rid of them. If they are, then I need to be a little bit more creative, maybe. And then providing a sense to which, what are the, so fine, maybe I go through and I leave this person in. But what types of people might my model not generalize well to? Okay, I've got a fine model. It's sort of modeling the relation between these different variables, but I've got a handful of multivariate outliers. So I can say, hey, this model looks pretty good within these bounds, but I've got a handful of people who this might not generalize well to. We've got a group of individuals that look to be sort of characterized by these types of characteristics. And it looks like this model doesn't generalize well. It doesn't predict my outcome well within people who have this configuration of characteristics. That's a really cool thing to know, and so a way to go through and start looking into future data, future projects. How do I go through? Okay, so I've got this set that fine, this works for the majority of people. Here's a group that's different in some way, marked by these sort of values on these different variables. Who are they, and how might I go through and help create a model that does a better job of understanding what's happening for this group? A regression, other analyses used to determine what variables are sort of contributing to this. Once we go through and we've identified what cases are coming up as unique, we can go through and sort of trick regression into telling us sort of what specific variables are contributing to that, which we can then go through and sort of say, okay, this case came up as unique within the set as a whole. Here's the characteristics that define those individuals. Okay. So going through and addressing these, first we want to determine the number and magnitude of extreme cases. Again, need to be very careful in terms of what the thresholds we're using to identify cases. We can use cut scores and rules of thumb. Those are great for help guiding decisions, but they should never be a hard and fast absolute rule, because what's going to happen is these are generally going to over-identify problematic things, and you're going to end up losing half your sample if you just go through and start pitching people indiscriminately. Okay, what you're going to do is your sample size is going to go down, and you're probably going to start to impact generalizability, because like unless you're perfect, unless you fit like right in my specific mold, then I'm going to throw you out. Well, now I've got a good model that accounts for just this narrow group of people, but anybody who's a little bit different than that, it doesn't account for. So it's this balance between not including people and sort of reducing the generalizability of your thing versus not throwing so many people out that then also reduces your generalizability, right? So you need to be careful in thinking about this. Also want to think about the impact on results with and without identifying, with and without your identifying cases, right? We've talked about this before. If my entire model and my entire pattern of results is based on Allison and Haley, then probably I don't have a very good model. The next person who tries to run this analysis is probably needed something very different, because I'm guessing that Allison and Haley aren't going to be in their sample, right? In this situation, I start to become concerned about the generalizability of my model, right? Now, what we would do here is if I identified Allison and Haley as problematic cases or unique cases in this sample, what I might do is I might run the model with them and the model without them, right? Now, the argument, as I said before, is that then this sort of encourages futzing around with my data and sort of including people in my set based on what they do sort of makes me happy in terms of my overall results. This is something we need to be very careful about. And honest with ourselves and our readers about why people were excluded or not, okay? Generally, if I've got two people with a reasonable sample or a handful of cases that completely changes things up, I should be hesitant to include those. There's gonna be times when like, having those three people in there makes your data look a lot better than without those, because then nothing much interesting is happening. Now you're kind of in an ethical battle with yourself on whether or not I tell anybody about this stuff. So just know, and so this is the argument against doing this, is that we can't trust people to make sort of ethical decisions based on things, right? So just be aware. One camp says, go through, have your criterion, make a determination on whether or not you include people or not, and then just go through, that's your decision, and then we'll go through and do stuff, right? Other camp is like, well, no reason to throw people out if their sort of inclusion, exclusion doesn't have any big impact on anything. So look at it with and without, and if it makes a big impact, then get rid of it. Problem is now, how do we put the genie back in that bottle if I know that it's sort of one decision that might not be statistically most defensible, give me something that's advantageous, right? I don't know. I come somewhere in between these two things, right? But those are kind of the different camps on this. Okay. Other thing to think about is addressing your extreme values can turn into a bit of a task, right? What what we want to do is if I go through and I address and find I have some multivariate outliers, I need to go through and I say, okay, these are the cases that I'm not going to include because of sort of these things. And so then I'm going to go through and get rid of those cases. So I go through and do that. Am I good to go now? Nope. What I need to go do through and now, okay, with my new set, I need to go through and take a look again, right? Because what can happen, we can have masking effects, is where I've got a case in there that doesn't look bad because I've got this other case in there that looks bad. But as soon as I get that case out, now all of a sudden this person that was kind of like hiding out in the bushes is now revealed, and now I've got to go through. What can happen is you can start to go endlessly sort of going through and sort of figuring things out. What you want to do is kind of take a realistic approach, say, this is never going to be perfect. So I'm always going to have some cases. I'm always going to have warts out there that are sort of maybe not perfect, and that's fine, but need to be sort of just very thoughtful in my approach to going through. Otherwise, I'm just going to go through and just like slowly chip away. And now I've got a sample of 50 when I started with 150 because I just iteratively removed everybody. Okay. So just be aware and be careful as you're going through and doing this, but also recognizing that once I go through and identify cases that are problematic, go through, pull those, what I need to go back through is then go through, take a look. So what can happen is I can go through, get rid of some cases that kind of impact the model, and then go through and take another look. And now I've got another handful of cases that are really screwing stuff up. They were less influential when I had the other folks in there to kind of balance things out. Without them, now things have gotten way out of bounds. And so now I need to get rid of those. And then hopefully at that point, you're probably good with stuff, but something to just keep in mind. Last thing, we'll finish up here. And we talked about this a little bit before, our linearity assumption, right? We assume that the relation between variables or some combination of variables is reasonably represented with a straight line, okay? We're gonna take a look at this with our bivariate plots and gonna use our theoretical conceptual knowledge and some evidence of non-normality to probably pick out specific pairs of variables that I'm going to go through and take a look at. With regression, if I've got, say, 6 different predictor variables and one outcome, and I'm looking at all possible combination bivariate plots of that, that's a lot, right? What we're going to do is we're going to generate scatter plot matrices to kind of just give us a quick look. And if something looks a little bit funky, we might go through and specifically plot those 2 variables. More variables you have in your model, the harder this gets and the more burdensome this becomes. But what we're going to do is if I go through and have a variable that has kind of a weird distribution, that's probably going to impact the bivariate relation. They're probably going to want to go through and take a look at that. So we're using the information that we've gotten before up to this point to make informed decisions on where we're going to focus our time and effort with this. Again, this linearity assumption critical for making a determinant on multivariate normality. Again, multivariate normality assumes that each variable and all possible linear combination of variables are normally distributed. Okay, we're looking here for linear relations that are homoscedastic. Okay, so here we have a linear relation. Here we have a nonlinear relation. Here we have something that's being thrown off by an extreme value. Here we've got something different and weird going on. We need to go through and figure out what's happening with that, right? In terms of solutions for if I do find a nonlinear relation between 2 variables, okay? First thing I can do is I can transform, right? We talked about transform. If I execute a transform, I'm essentially modeling a nonlinear relation between 2 variables. And this is a fine thing to do, okay? Other thing that I might do is I might dummy code a variable. So you say, this is high, this is low. If I look at this here, right, I've got a very strong relation between X and Y. If I just try and look at a linear relation between these 2 variables, it's going to be 0, right? It's just going to tell me that X is unrelated to Y. That's clearly not the case. X is very, very tightly correlated with or associated with Y. It's just in a nonlinear fashion, okay? But if I go through and I dummy code this, maybe I don't want to go through and model the actual nonlinear relation because it makes my model complicated. What I might do is I might say, you know what I'm going to do is I'm going to sort of truncate X from this range to that range and from that range to that range. Now all of a sudden I've got this, it's pretty well represented by a linear model. I've got this, it's really well represented by a linear model. And what I've got now is kind of a piecewise function where I'm modeling the relation between X and Y on X values ranging from -5 to 0. And then a separate model that captures the relation between X and Y from 0 to 5. Okay, so we can start to dummy code and break things up. We can run a nonlinear model. So now I'm not going through and transforming, I'm including a X squared value in there and using that. And so now I'm just using a nonlinear regression to go through and account for this, which is perfectly fine. It just makes things a little bit more complicated to understand or to model or to interpret. Other thing I can do is I might just ignore. Okay. Here, what we need to do is, let's say I've got a case that looks something like this, right? With these data, if I go through and I model a parabola here, like an inverse quadratic, right? With this set of data, it looks like fit that pretty good, right? But in the back of my mind, what I should always be thinking about is wondering, is there a reason I should expect X and Y to hold a nonlinear relation? And what I'm looking at in this graph, is this just something that's is this just like a unique pattern of scores that fell out in this data set? Because what I don't want to do is apply a nonlinear model to a sublinear variables that just happen to look like they might have nonlinearity in this set that I collected. Okay, something like this is very clear, right? This maybe less. It looks like we've got an exponential function, something going on there, right? This, I don't know, right? I mean, it's maybe, and I can go through and I can estimate this with a linear function, and that linear function is going to fit pretty good. Okay, if I go through and I take a look and I include a quadratic term in there, maybe it goes through an increase in my R squared by, a couple tenths of a percent, or say maybe a couple percent, right? Then the question is it worth the added complexity to my model to add like 2 percentage points on an R squared in order to model that nonlinearity, if I'm not 100% certain that that's something real that actually exists in the population versus something that just is a weird configuration that happened to show up on my data set. Okay. But this is where knowing your research area, knowing kind of having a good conceptual understanding of what's going on with your data starts to become important in trying to make that decision. All right, we'll finish up there. We'll pick up with variance assumptions. Okay, and then you get in there. All right, we're making decent progress with stuff. All right. Couple more things, but it won't take us too long to get through that. Okay. Questions on anything we covered up to this point? Problem set 1, where we're at with stuff, anything along those lines?
Are you looking me right in the eye?
I don't know, like I was getting an intense, I was like, looked like you were waiting to jump on with the question.
Later.
Yes, absolutely.
I do have a question that
Yeah.
maybe just reading into it too much, but on problem like 1 and 2, you say options.
Yeah.
Discuss the various options.
Yeah.
So not singular but plural. What is there supposed to be more than one option on both of those?
Carefully to see if you have options, yeah.
Okay.
But you're opposed to us making like a dichotomous variable out of a continuous.
Yeah, don't do that. Don't, because then like the options are endless, right? Then I'm gonna do extra. No. We're just using the variables that you have. Okay.
And are we doing it based off like, so for example, in that first PowerPoint presentation, like lecture that we had, you gave us like really handy dandy tables.
Yeah, that was a handy dandy table.
Both of
Like
them.
that would be helpful
Now,
for this.
if we look at those, we're still able to identify options.
Probably.
Okay.
Yes, please don't come up with weird things that you can use the variables to start opening up your options for other things. Yep, just the ones you got there, okay? Awesome. All right, any other questions?
No.
Yes, all right, thanks, folks, and have a good evening.
Okay, so what like.
Okay.
Can I ask you this, my eyes
Yeah.
are not yours, Yeah.
Yeah, so I did say both. And then.
Yeah.
For the second show, I'm all